T-minus 1 minute. T-minus 30 seconds. We are go for launch. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Good morning and welcome to NASA's Lunabotics 2025 finals event. This is day 3 of 3 days of competing here on the Space Coast of Florida. We are broadcasting live from this amazing Center for Space Exploration facility here inside NASA's Kennedy Space Center Visitor Complex in Florida. My name is Kurt Lloyd. I'm a software developer and a robotics researcher here at KSC, and I'm happy to be your MC, your narrator, your color commentator for this entire event. I want to give a big shout out to all the teams and the staff and the guests that are here in this building. It looks a little light on students behind me, but the students are coming in right now in order to get their robots prepared for today's competition runs. We're also super excited for everyone who is watching this live stream from all around the world. Thank you so much for your interest in NASA and for your interest in this event. And please don't be shy about sharing our live stream link with everyone you know. Speaking of guests watching from around the world, if you're not familiar with NASA's Lunabotics event, I'll quickly summarize it for you. Lunabotics gives college and university student teams, like those you're seeing behind me, the task of designing and building working prototype lunar construction robots. During the robotic competition runs that you're going to witness today, these robots are going to traverse complex and rugged terrain, and they'll dig and they'll transport fine particulate material, which is simulating moon dust, from one location to another location. It's an exciting competition, and I'll be here the whole time to explain what's going on. Last week, we had 35 teams compete in the Lunabotics qualifying event at the University of Central Florida in Central Florida in Orlando. And the top 10 teams from that event are performing here this week at the Kennedy Space Center Visitor Complex. These 10 teams that you'll see growing behind me as they come in for the morning, those 10 teams are about to compete and have been competing for the last 2 days for the grand prize in NASA Lunabotics 2025 finals event. Now let's review what has happened so far. We started this event on Tuesday, the finalist event for the top 10 teams. And so on Tuesday, we ran 6 of our 10 teams through their first of 2 attempts, their first of 2 runs. Then yesterday morning, we got through the other 4 of the 10 teams. Then yesterday afternoon, we got through 4 teams' second run. That's their final run of this finals event, which leaves 6 teams for us to get through today, to get through their second of 2 competition runs. Today, you are going to see the University of Utah, Colorado School of Mines, Purdue, University of Illinois Chicago, University of Akron, and College of DuPage. These are the 6 teams remaining to get in their second run attempt in this year's finals competition. Then, as soon as we're finished with the final run today, College of DuPage, we will give our judges about an hour in order to verify their scores and do their calculations, their final calculations. And so roughly about an hour after the College of DuPage is finished this afternoon, we will have an awards ceremony, an awards presentation right here in this room. We will live broadcast all 6 of these teams' runs today. In addition, we will broadcast the award ceremony right here on this stream. We won't even change the URL. Speaking of the URL, if you missed our broadcast on Tuesday or yesterday, Wednesday, those recordings are on Kennedy Space Center's NASA Kennedy's YouTube channel, which is where we're broadcasting today. You do need to, if you're looking for those on Kennedy's YouTube channel, you do need to click on the live tab because we did live stream those, and we're live streaming this one also. So later on, when you, if you want to go back and look at something from one of our live streams, they can be found under the live tab in NASA Kennedy's YouTube channel. I did mention that there were 35 teams that competed last week at the University of Central Florida, and only the top 10 you're seeing here this week. The top 10 teams in alphabetical order are College of DuPage, Colorado School of Mines, Michigan Tech, Milwaukee School of Engineering, Purdue University, the University of Akron, the University of Alabama, University of Illinois Chicago, University of Utah, and University of Virginia. But there were 25 teams that that we haven't really been focusing on this week because we've been focusing on these top 10. So I want to give credit to the other 25 teams who have worked really hard all for the entire academic year, ever since, since August till now. All 35 of these teams, not just the 10 that we've been focusing on, have worked really hard. They have designed a robot. They've performed engineering trades on what to include and not to include on the robot. They've performed trades on different types of excavation technologies, different types of mobility or driving technologies. They've performed trades on how much automation and what sensors they're going to put on the robot, what kind of software they're going to put on the robot. It's a big deal. These students are basically performing a very detailed NASA systems engineering design process, and that's a big deal. And so all of these teams did compete last week in the qualifying rounds at the University of Central Florida. So I want to give credit to the teams that are not here this week but did compete last week. That includes Auburn University, Boise State University, Cleveland State University, Drexel University, Embry-Riddle Aeronautical University, Florida International University, Inter-American University of Puerto Rico, Bayamon, Marquette University, New York University Tandon School of Engineering, Southern Illinois University, Carbondale, State University of New York at Buffalo, also known as University at Buffalo, Temple University, Texas A&M University, the United States Military Academy, University of Houston, Clear Lake, University of Maine, University of Miami, University of Nebraska, Lincoln, University of New Hampshire, University of North Carolina at Charlotte, University of Portland, University of Rochester, University of Tennessee, Knoxville, Virginia State University, and Virginia Tech. I think we should give a big round of applause to all 35 teams that have competed this year in NASA's Lunabotics competition. All right, as we wait for everything to get set up here, if you cut to the team that is getting ready in their pits, we have in the pits, that's the Colorado team, right? Wave hello. Sorry, I'm on the wrong page here. I've got the Utah team right here next to me. I've got the Colorado team back there on camera right now. These two teams are working hard in the pits right now, getting their robots ready to go because they are the first two robots that are going to run this morning. Looking at the Utah team's body language right next to me, it appears that they're about to load the robot onto a cart so that they can get it over to the inspection station and then get the robot into the arena to run. So these teams are just getting going, but it shouldn't be long before these teams get in the arena and start their runs. And we will definitely be broadcasting and narrating along when that happens. I was doing some it's really hard to take in the actual data live when you're watching these teams. But earlier, I was kind of looking back at what we had seen. We haven't really been broadcasting the actual number of the size of the berms, the size of the dirt piles that these teams have collected to the broadcast. But here in the pits, we're showing these numbers up on the screen to all these teams. So these teams are aware. And just to summarize, the three teams that have the top, that have brought back the largest pile of material into the scoring zone during their first run, those teams are the University of Utah, University of Illinois Chicago, and the University of Virginia. Now, just because a team brought back the largest pile of soil or Luna regolith doesn't guarantee that they're going to win this competition. A really big critical thing is whether these teams are doing autonomy during that time, and if they are doing autonomy, how much autonomy, because there are different levels of autonomy. And so here in the pits, when we're watching a team perform live on the screens here, we don't really have perfect knowledge of whether a team is performing autonomy or not. We have subtle hints by watching the students in the control room, which I have we do cut to that occasionally, but I do have a monitor in front of me where I can just watch those students and see whether they're completely hands off. I will say though that the judges in the mission control room know for sure. They are the ones that are actually communicating directly with the students. I'm just kind of interpreting some body language, so I could be wrong. But what it seemed like to us as a spectator of the teams that had done at least some autonomy during their first run, it looked to us like Michigan Tech had done some autonomy, Purdue University, University of Akron, and the University of Alabama. It looks like these four teams did at least some level of autonomy, and we don't know exactly how much, and that is key. How much autonomy those teams actually did and got credit for on the score sheet is really pivotal and really key to this competition. It is completely possible. It is highly, highly possible that a team that these four teams that did some level of autonomy, their final score is larger than a team that brought more regolith simulant into the scoring zone without autonomy. I hope I'm not being too confusing. It's more important to bring a little bit of dirt, regolith, into scoring zone with autonomy than it is to bring a lot of regolith into the scoring zone without autonomy. The scoring, and the teams all know this because it's all documented in the rules, the scoring really, really leans toward. It gives a lot more points toward teams that do autonomy. So I love that the Utah and the U of I Chicago and the University of Virginia teams ended up bringing the largest amount of material. They should be super, super proud that they did that. Without autonomy, though, we really need to be looking at the teams that did autonomy to try and, do some armchair analysis to try and find out which team is going to run away with the top prize. And so far, it looks like the teams that have done autonomy have been Michigan Tech, Purdue, Akron, and Alabama. So two of those four teams that did autonomy are still going to have a second run today. Two of those teams did already have their second run yesterday. So Michigan Tech and Alabama have both yesterday have both done both of their runs. They are basically finished with this competition. And so the question of which one of those teams is on top, we don't know. We did notice that Michigan Tech brought more regolith to the scoring zone in their second run than Alabama. But which team did more autonomy, that's really going to be the key. That's going to be what wins this competition. So with that overview, I hope I didn't confuse anybody with that kind of detail, but that's kind of the situation that we're in. That's the details that these student competitors are thinking about and focusing on because they know how the scoring works. It was all published in the rules. And so I think we're in for an exciting finale to our competition with 6 teams running today and then a short break. I should mention we are going to take a break at lunch. And, I forgot to mention, we will take a lunch break. And during that lunch break, we're going to give a Robot Innovation and Survey prize. So we're going to have a little mini award ceremony during lunch today, just like we did yesterday and the day before. So 6 teams running today, a quick break for score verification, and then an award ceremony. That's what's on tap for today as we see more and more teams coming in behind me. So let's just watch the preparations that are happening here and watch the student teams as they get their robots ready to compete in today, the final day of NASA's Lunabotics 2025 finals event. Thanks for watching. Don't go anywhere.
Did you know there's been over 1 million registrations in NASA's virtual guest program since May 2020? From your neighbor to the Crew 5 astronauts, you might be surprised who is a NASA virtual guest.
Do you have Mars 2020?
I do. Do you have James Webb?
Sure do. Do you have Crew 5?
Well, I've got it here, and you guys have it here, but I missed it here.
We conducted over 200 science experiments and technology demonstrations on our mission. We love being part of Expedition 68. We even remembered a virtual guest passport for Einstein, our freefall indicator, but we forgot to register and missed the stamp.
Even if you're doing existing research, never miss a stamp from NASA's virtual guest program. Whether you're en route to the International Space Station or located anywhere around the globe, register at nasa.gov/virtual guests to receive updates on missions and milestones. As a virtual guest, you will receive curated resources and a stamp for your passport following a successful launch.
Remember, you only get the updates and stamp if you register.
I joined. I won't miss it next time.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills.
It's been 50 years since we've been to the moon, and we've got a great program called Artemis. We're going back. The Apollo program was a test for the American people that you can do what you set out to do. All it took was turning to it and making it happen.
We are go for a mission to the moon at this time.
Engines on 5, 4, 3, 2, all engines running. Launch commit, liftoff. We have liftoff 49 minutes past the hour.
I think the characteristic that I remember most of the Saturn V was the noise. The noise was enormous and it was almost impossible to communicate.
We're go, same tide, we're go.
Tranquility Base here. The Eagle has landed.
The landing to me was a great celebration. The nation was almost euphoric.
That's one small step for man, one giant leap for mankind.
There are so many things that we could eventually learn about our universe and the spacecraft that we use exploring.
We are a nation of explorers. During Apollo, we were on national TV literally every day because we were doing something visible that Americans could see and they could feel and say, look what we are doing. And I believe Artemis is going to come up and say, look what we are capable of and what we are doing now.
Artemis will stand on the shoulders of Apollo. They're going to have the eyes of the world on them when they start down this trail.
The science of a space flight is one that will continue to inspire. Going to the moon generates technology, more communications, more computer technology, more sophistication in manufacturing that help us in everyday life.
We have a generation that is ready, a generation with that technology, a generation with the education. Artemis represents the future in space. It is our next big step, and it is time to take it.
The crawler transporter is it's a machine that goes and picks up the mobile launcher, the SLS rocket with Orion. It's basically the cornerstone of the mobile launch concept. Without the crawler, you couldn't transport the mobile launcher and the vehicle from the VAB to the pad or the pad back to the VAB. And it was designed and built for the Apollo program to move Saturn V's to the launch pad. Since then, we've modified it and used it to move the entire shuttle program. And after the shuttle program, we did extensive modifications, and now it's to be used to move Artemis to the launch pad. The crawler is 136 feet long from end to end. It's 114 feet wide from the edge of the truck to the other edge of the truck. It weighs 6.6 million pounds. It has the power to do 2 miles an hour, but you never want to go that fast. Generally, we're around 0.83 for SLS. Artemis will be one of the heaviest loads we've ever carried and one of the tallest loads we've carried. I am exceptionally proud of our team. They're very talented, they're very committed, and they're just all around good team. I think any problem that crops up or anything that comes up, we'll fix it and we'll get moving again. And again, it starts right here with the crawler. So if we do our job and everybody else does theirs, man, we're gonna have a successful launch. We're going back to the moon. This is gonna be just fantastic.
The imagery that we're collecting on Artemis 1 and the mission itself is preparing to carry humans to the moon. The Orion Imager team is going to be monitoring every aspect of visual spacecraft performance for the entire duration of the mission. The first time that we're going to be live streaming digital video from a human piloted spacecraft back down to the Earth from the vicinity of the moon. That's never been done before. What we'll be transmitting live streaming will be lower resolution, more compressed, because we have to fit it into a thinner pipe, if you will. Every one of these cameras is in its position where it is and is configured the way it is for a very specific reason. We're going to be monitoring anything that we can see with the cameras for spacecraft performance. The imagery teams at NASA are composed of dozens and dozens of very highly trained, very specialized people, engineers, technicians, analysts. If we can see it, we're going to try and keep an eye on it. Imagery has been invaluable throughout the history of NASA. We flew cameras on Mercury, Gemini, Apollo, all of that stuff that we saw with the astronauts around the moon. It helps us detect the unknown unknowns. It allows us to see things that we didn't anticipate happening before. So when we do fly people on Artemis 2, we can have a high confidence that everything is working the way it should.
Our moon It seems so close in the night sky, but getting there is really hard. But what if there was a way to change that? Only a few nations have successfully landed on the moon. As NASA sends astronauts back to the lunar surface, this time to stay, we will need to send science and technology instruments ahead of time to lay the foundation for human exploration. To make this happen, NASA is helping establish a commercial lunar economy. For the first time ever, there will be commercial delivery services to the moon. We are enabling American companies to send our payloads to the lunar surface for us. These delivery services will expand our capabilities for exploration, radically increasing the amount of science we can achieve. This high-risk, high-reward initiative will invest in and leverage the entrepreneurial spirit of American innovation to launch a commercial lunar marketplace, advancing technology and exploration for all of us. With this never-before-seen streamlined access to the moon, we will be able to make novel measurements and develop technologies that scientists have long wanted to do on the lunar surface. And as this new industry matures, this commercial delivery service for NASA and other customers could expand beyond the moon to other destinations in our solar system, and we can learn to live on another world because we are explorers.
Hi, I'm Janet Petro, the director of NASA's Kennedy Space Center in Florida. Hop in and let me show you what we're doing at Earth's premier spaceport. Let's go fly. Our spaceport is proud to support the agency's goals to return to the moon in preparation for Mars. Our cooperation with commercial companies and international partners is greater than ever before as NASA embarks on a new and exciting era of space exploration. At Launch Complex 39B, the uncrewed launch of Artemis 1 was an exciting first step on our way back to the moon. Now, we are hard at work preparing the hardware, systems, and processes for the crewed Artemis 2 mission. Targeted for 2025, Artemis 2 will crew the Orion spacecraft and the Space Launch System rocket when the 4-astronaut crew ventures around the moon on a 10-day flight and returns safely to Earth. Meanwhile, we are launching missions to the International Space Station, continuing the research that helps us solve problems on Earth while proving capabilities we need for long-duration human space exploration. Microgravity, low Earth orbit, offers a unique environment to study disease formation, test diagnostic tools and treatments, and advanced technologies like computers and robotics. NASA and our commercial partners are expanding the ability to launch crews, science, and cargo to the orbiting laboratory, which will ensure sustainable operations on the station for years to come. Nearby, in the Space Systems Processing Facility, teams are developing other exciting technologies we will need to live and work on the moon. Plant researchers are experimenting with new ways to grow food in space, and engineers are working on projects like 3D printing capability to build structures on the moon, rovers and instruments to find resources to help sustain a long-term presence, and electrodynamic dust shield technology that can repel the abrasive moon dust to protect our astronauts, their vehicles, and sensitive equipment. NASA's commercial providers help us launch a range of science missions that study our Earth, explore other planetary bodies, and reveal more about the origins of life and our universe. NASA works with both emerging and established commercial providers for launch and landing opportunities. These efforts benefit the U.S. economy and help grow the commercial market. By helping commercialize low Earth and cislunar orbits, NASA can reduce the cost to explore space and maximize benefits here on Earth. Another Kennedy team in the Space Systems Processing Facility is developing NASA's deep space commercial supply chain to procure the services needed to transport cargo, equipment, and consumables needed for human exploration of the Moon and Mars. For Artemis 3 and beyond, NASA will rely on commercial partners to support a regular cadence of moon landings. Our commercial partners are doing exciting work to develop the next generation of spacecraft and landers. The spaceport offers a prime location for companies like these to consolidate their manufacturing, testing, integration, and launch services in one location, helping them save costs while leveraging the spaceport's unique expertise and capabilities. Kennedy has supported growth at the spaceport through key power, water, and transportation upgrades and investments in fiber telecommunications. Through our master planning process, we will continue to forecast and plan improvements to enable responsible development into the future. And I couldn't be more proud of all the people at the Kennedy Space Center who make this all happen. You know, the processing, the integration, the launch operations, all carefully working together with our partners, with the Space Force, and with our NASA programs. The future's coming fast. Kennedy Space Center is leading the way. We're not just launching humanity's future, we're launching to the moon and beyond.
You are watching NASA's Lunabotics 2025 finals. Students are preparing the robots for their second and final runs. We did switch up the schedule just a little bit, and the College of DuPage is going to run first today. So in just a few minutes, we should see the College of DuPage students and their robot enter the arena, and students enter the mission control room. So DuPage is going to run first, and then University of Utah, and then Colorado School of Mines. We will likely have a lunch break and a quick award ceremony during that lunch break. And then this afternoon, we will run Purdue, University of Illinois Chicago, and University of Akron. After Akron, at the end of our, towards the end of our day, after Akron has run, we do have a break while the judges verify their scores, but we have a special add-on. During that break, we have some university teams that are going to give a short presentation. So that will happen between our runs and the official award ceremony. And as soon as the judges have verified their scores, we will have the official award ceremony later tonight. The award ceremony should be around 5 p.m. Eastern, but our schedule is very fluid, and the award ceremony is going to happen as soon as our judges hand us some official-looking pieces of paper and tell us that they are done verifying the scores and give us their results. So that is the current schedule for today. A little fluid, but this is what we're going with right now. DuPage will be coming up first, then Utah, then Colorado. Lunch break with a mini award ceremony. And then this afternoon we will run Purdue, University of Illinois Chicago, and the University of Akron. And then we will have our award ceremony after that as soon as we are ready. So don't go anywhere. Keep watching. And we look forward to DuPage coming up first this morning to run their second of 2 official scored competition runs in NASA's Lunabotics 2025 finals event, live streaming here this week from NASA's Kennedy Space Center Visitor Complex. you're seeing on the screen right now are the DuPage team students that are getting ready to control their robot from our mission control room. There are also DuPage students right now in the arena that are near the robot just in case a switch needs to be switched, a button needs to be pushed, a reboot needs to happen. All teams get a 10-minute setup period to set up all of their equipment in the mission control room and all the equipment in the arena, basically the robot, and get it all verified working. We did see some movement from this DuPage robot a couple minutes ago, so it does appear that this robot is ready to go. You can see the students have signed the front bucket of their robot. The word CAN bus is a very common thing in the robotics industry. It's also in the automotive industry. A CAN bus is a real-time network used in the automotive industry and the robotics industry. Fiducial is an interesting word. That's a fancy word for the barcodes that are placed around the arena. So a fiducial system is a visual system that robots will use to visually detect barcodes in order to calculate where they are in 3D space. We can see the DuPage students are leaving the arena, an indication that the robot's ready and they're ready to start this run, the second run for the DuPage team. All of our runs today are going to be second and final runs for these 6 teams that remain. So our arena judges and our mission control judges are going through their checklists and making sure their team is ready and their facilities are ready before they notify the timing judge to start the timer. There's going to be a 30-minute timer that will start, and then these DuPage students will start driving the robot. I believe the DuPage team will be manually driving this robot. This robot does have some sensors, obviously, so let me take that back. Could go either way. They're set up for a possible autonomous run, so we will keep our eyes on the students who are quote-unquote driving this robot during their 30-minute run, and we'll pay close attention to whether those students are controlling this robot manually or just sitting back and enjoying watching the robot control itself. All the students, all the teams that compete in the Lunabotics event know that autonomous runs, even partial autonomous runs, are worth a lot of points. And so it does give a team a fighting chance if they do try autonomy, even if they're not 100% certain that it's going to work. It is a risk that is worth trying. So hopefully we'll get to see this DuPage robot attempt at least some level of autonomy in the second run. It is not uncommon in this competition for a team to perform their first run manually and their second run autonomously because they know they can score points manually and they maybe have less confidence in their autonomous systems, which include sensors and software and logic and power and wiring, and autonomy is not trivial, not easy, and we have made it a very important part of this competition. The robot is moving. Okay, the timer has started. The robot was driven via joystick right up to that visual target right off the bat. And now the student appears to be typing into their keyboard, possibly launching an autonomy process on board the robot. Yep, that's exactly what happened. We saw a button press. We see the robot moving on its own. And sadly, it drove right into those rocks. Now, the robot appears to have a black puck that is likely a LiDAR or a laser scanner, but when that robot hit the rock, I think the students took over manual control. It's a little hard to see. I'm trying to control 3 different cameras here. I apologize. Oh, it looks like it's a little bit. Okay, it came out of it. Its tracks were a little buried there for a second. Now this blade, that's a crater, by the way. This robot drove into a crater, and that's kind of another crater right there. When this robot drove into a crater and the blade hit pretty hard, the tracks spun there for a second, and that worried me, but it did get out of it, thankfully. So we're 2.5 minutes into this run. The team is lining the robot up for a dig, and as long as they start their bucket digging to the left of that line, that orange chalk line, and then push the material into the scoring zone, which is in the middle of the 4 orange and white posts. Yeah, the student is definitely driving now. The joystick finally came into view. So right now, one of the DuPage students is manually driving this robot. In order to get material into the scoring zone. For anyone who's kind of new to our broadcast, this event starts with a robot in the starting zone, and teams have 30 minutes to get from the starting zone across an obstacle zone that is filled with rocks and craters, and then excavate or dig simulated lunar soil in our excavation zone, which is where the robot is right now, and then move that simulated lunar soil and deposit it into the scoring zone, which is in the lower right. I'm sorry, I'm looking at the wrong camera. My bad. The excavation zone is in the upper right of the screen, and the scoring zone is where the blade is right now, in between those 4 vertical orange and white posts. So this camera view actually shows the entire arena. You can see where the robot started in the upper left, and you can see its tracks heading off to the right through the obstacle zone in the upper right into the digging zone, which is where the robot is right now. So that's that's basically the entire operation that all of these competing robots are going through, is getting pass the obstacle zone without hitting rocks, without falling into craters, and then scoring as much material as they can from the excavation zone into the scoring zone. But this competition is more than just calculating how much material they brought into the scoring zone. That's just one variable that goes into our score sheet. Whether a team does certain parts of that operation autonomously or not is a really, really big part of our scoring system. Also, it's not just as simple as comparing how much simulated lunar soil each team brings into the scoring zone. We also take into account the weight or mass of each robot, and we take into account how much power each robot used to move that material into the scoring zone. So it is completely possible for a large robot that uses a lot of power and brings in a lot of material to get the same score as a small robot that uses a little power to bring a lot less material into the scoring zone. It's technically possible for those two scenarios to end up with the same score. And that's part of the trade-off that all of these teams have to make when they're designing, building, and testing their robots. Do we want to build a large robot that uses more power, but we know it can bring more material? Do we want to use a small robot that uses less power, maybe can't bring as much material? Is there some magic solution where a small robot that uses very little power can bring in a lot of material? That's the secret sauce that all of these teams are trying to find. But there's also the variable of autonomy. We have purposely chosen to make autonomy a very highly a very critical part of our scoring system. And so even a robot that doesn't bring very much soil into the scoring zone, if it does so autonomy, that can actually score higher than a robot that manually brings a lot of material into the scoring zone. And the teams know this up front, so they're really all the teams that have made it this far into the top 10 have at least tried some amount of autonomy at some point to get here competing this week. I suspect today, since these are all the second and final runs for all of our teams that we're going to see today, I suspect we'll see teams that didn't try autonomy on their first run. We'll actually see them trying autonomy on their second run, which we did see this DuPage team. They did try and start out at the beginning of this run with some autonomy, but it did not appear to work, sadly, and so it's looking like this entire 30-minute run might end up being a manually driven robot, which is still great experience for these teams. And they're learning lessons that they can hand down to next year's team. And what you'll notice with a blade robot like this, a dozer blade, is that if you push the blade down too far, your mobility system, tracks in this case, can't overcome the stress, and that's what you just saw there. The tracks were spinning freely, and so they lifted up the dozer blade a little bit, and the robot was able to make some progress. So dozer blades can be very productive, but they do require finesse in driving, in getting the forces counteracted appropriately. Now, a tracked vehicle like this has a lot of surface area that is in contact with the surface, which gives you a lot of potential for moving this robot. Don't forget, though, that the top few inches of this simulated lunar material is light and fluffy, so that actually can be harder. Let's say you might have to doze very lightly and just skim small layers off the surface to begin with, because the fluffiness of the soil is going to make it harder for your tracks to really get a good grip. But once you get down to the hard stuff, a few inches down, I believe that I could be wrong, but I believe your tracks probably are going to get more grip once you get down to once you get past the fluffy stuff. So many variables that all of these teams have to concern themselves with and learn potentially in real time if they don't have a similar lunar simulant material to practice on back home. I mentioned that each team gets 2 official competition runs, 2 scored runs this week, and I do want to mention that no teams are allowed to practice in this lunar simulant that we have here. So their 2 competition runs are potentially the first time these robots have ever encountered this particular lunar soil simulant or Regulus simulant. There are a few teams that have similar lunar simulants back at their school, but it's not super common for a university to have this sort of program that would have a need for and access to this sort of high-fidelity lunar soil simulant, which means a large percentage of our teams are experiencing this simulant for the very first time on their very first official run. So there's so many variables in this competition that make it so hard. These teams are seriously in the big leagues when they compete here. These 10 teams, along with 25 others, 35 total, competed last week in the Lunabotics qualifying rounds at the University of Central Florida. Their simulant is a little bit different from ours. Depending on who you ask, I've heard that it's a little bit easier to drive on and a little bit easier to dig in. Their distribution of particle sizes is particle size in their simulant is a little bit different from ours, and I believe I've heard opinions that our lunar simulant is a little bit harder for these robots to handle, to do productive work in. All right, this robot from DuPage does appear to be doing productive work. From the side camera view, we should be able to get a feel for the piles that they've brought in. It's really hard, even from this side view, to tell how big these piles are, because it's just a lot of gray, and the lighting is not providing a lot of good shadows. But I believe this team is going to be proud of what this robot has done. both in this run and their first run earlier. Regardless of their final score and outcome. All of these students, regardless of the outcome, are learning so much throughout this entire school year. They're designing robots, buying parts, building parts, performing design reviews for their faculty and advisors and peers. Actually going through the motions of building a complete robot that is capable of an operation that we're actually going to need on the moon. We're going to need to be able to traverse an obstacle field, and we're going to need to be able to excavate this lunar soil, which has very unique physical properties. It makes it hard to drive on and hard to dig in. So these students are, and then they get to compete here in front of the world. And right here at the Kennedy Space Center, they got to watch a rocket launch the other night. So regardless of the outcome, I think it's safe to say that all of these students are having a really great experience. They're going to be able to put this on their resumes and get snatched up by companies in the space industry, in the aerospace industry, any industry really. These students are gaining mechanical skills, electrical, software, automation and autonomy skills. And that's just the technical skills they're learning throughout this competition, throughout this year's journey. They're learning how to work with others, not just others in their own skill set or their own degree area. Robotics includes lots of different skill sets and degrees working together. That is a life skill that is going to really become useful in these students' future careers. DuPage is down to under 10 minutes remaining in their second and final round. As long as they lower their bucket on the excavation, in the excavation quadrant, they're allowed to push material all the way into the scoring zone. They just have to start the excavation over in the excavation quadrant. "11 minutes left for College of DuPage. In order to calculate how much material a team's robot has brought into the scoring zone, we have a laser scanning system overhead that will scan the area in between these 4 orange posts that you see on the screen. We'll scan that area before the run starts, and then it will scan the area again after the run, and it gets 2 point clouds from those 2 scans, and it can calculate the area, the volume rather, between those two point clouds, between those two 3D surfaces. So highly technical engineering software that can laser scan a surface to a high degree of accuracy and can calculate the space between those two surfaces, the volume of material that a team's robot has brought into the scoring zone. Very similar technology to the LiDAR pucks that we see installed on a lot of these robots. That's probably a LiDAR puck. The black hockey puck shaped device mounted high on top of this, at the top of this robot, is very likely a LiDAR, a laser scanner that can scan all the way around this robot, 360 degrees, and usually they provide a 3D surface for the robot to decide if there are rocks or craters in that 3D surface that the robot needs to avoid. Can also be used to scan the entire arena and decide what's the safest path to drive from point A to point B. And then in this view, near the starting, in the starting zone, which is the upper left of the screen, you can see a black and white pattern, which is a barcode, technically called a fiducial. That black and white barcode is typically used in autonomous robots, and a run-of-the-mill black and white webcam can easily look at a black and white image like that from far away, from near or from far away, and it can use simple math, simple trigonometry in order to calculate the robot's position in 3D space, in X, Y, Z coordinates. And it doesn't take a lot of processing power either to do that. So simple cameras and simple black and white or even colored patterns placed in known positions and of known sizes can pretty easily, pretty quickly and pretty easily tell a robot where it is in 3D space. Kind of cool technology. How might we use that technology on the moon? Well, not shown in this image might be a lander that had dropped this robot off over there in the starting position. And so on that lander, you might put your visual indicators, your barcodes, and then as your robot drives away from the lander or around the lander, it can look back and see that barcode and say, oh, I'm 20 meters away from the lander and 20 degrees off the center line. Or, of course, there is a limit to a visual indicator like this. Here on Earth, we rely heavily on GPS satellites to tell us where we are on the Earth. GPS satellites don't exist on the moon yet, but I suspect that someday we will have a lunar positioning system that will make it almost trivial for any robot or any astronaut explorer to know exactly where they are on the lunar surface. But until then, we'll start with visual indicators like you see here on this slide feed. We're coming up on 5 minutes remaining for College of DuPage. They continue to make progress. They continue to push bladefuls of material into the scoring zone. this entire run appears to have been performed manually by the students. So it appears that DuPage is likely not getting autonomy points. For this run. Not to imply that the students are sad about that. The students are positive, having a good time. They're doing their job. They're continuing to push as much material as they can into the scoring zone. They do not appear to be stressed or sad at all with the outcome of this run. 4 minutes remaining for College of DuPage. Again, during this second run, there's a significant amount of simulated regolith that is sticking to the front of this blade. A surprising amount. It shows how sticky this stuff is, even though it's not damp at all. There's very little moisture, if any, in this material. It sticks together so well. It sticks to itself so well. Because the particles are very jagged and they lock together like puzzle pieces. Why this material is sticking to the blade so well, I'm not sure. It'd be interesting to look at this blade in detail later and see if there's any texture that might be holding on to this material, or if the blade is smooth, then it's just the lip at the bottom of the blade that is just providing a ledge for the material not to fall off of, which is possibly the case. Not necessarily a problem for this robot, just an interesting artifact of this design. Minute and a half remaining. The students are still making good progress on pushing material into the scoring zone from the excavation zone. One minute left for DuPage. Seconds. They're being a little bit aggressive right here. Yep. They need a little bit of aggressiveness just to get some material now in the last few seconds. Hopefully they'll get a little bit more into the scoring zone. All right. as the seconds wind down, let's give College of DuPage a big round of applause for this effort. You can see the students are pleased with what they've done, and we've got a side camera that kind of shows the amount of material that that they've put into the scoring zone. Although the camera doesn't do it justice. If you were to be in there, with your three-dimensional eye vision system, you would see that it's a lot more than it looks like on camera, thanks to the 2D and the low contrast, and everything's gray. That's always a problem with vision, is getting the right amount of contrast, and that's why a lot of these robots don't just depend on a 2D camera for vision. That's why a lot of them have 3D laser scanners that can really truly tell you the true details of the 3D surface around the robot. So as the DuPage team comes into the arena to clean up the robot, and as the judges get the arena ready for the next team is going to be the University of Utah. They have left the pit area. They've gone through their inspections. They've gotten all suited up in their PPE, and there they are inside the arena with their robot, ready to start their run. And so it's going to take our judging staff a few minutes to recycle the arena and to recycle the Mission Control Center. So stand by, don't go anywhere, because you don't want to miss the University of Utah coming up next on NASA's Lunabotics 2025 Finals Event, Day 3 of 3, our final day, streaming live from Kennedy Space Center Visitors Complex here in Florida. Don't go anywhere. We're watching the University of Utah students in the arena putting the final touches on their robot. We saw some movement from the robot earlier, indicating that commands are working. And the students appear to be doing some more detailed verifications before they exit the arena. This Utah team, during their first run, were very productive. It is not a surprise to anyone here on site that this Utah team brought the most material into the scoring zone during the first round than any other team. So this Utah was top of their field in just scoring material during their first run. They did perform that first run manually. And it does appear this robot has some autonomous systems. The students in the arena have placed visual targets around the starting area. And we noticed some cameras on the front of this robot that appear to be more than just simple webcams, which technically is all that's needed to look at the visual targets. But they appear to be depth cameras or 3D cameras that will tell you, that will basically give you a 3D surface rather than just a 2D image. And so there is a non-zero chance that this Utah team is about to try some autonomy during their second run. They know manually driven that they can do amazing work, which they proved earlier in this event. Hopefully, using autonomy, this team will also be able to bring enough material into the scoring zone under autonomy to really be competitive against the other autonomous systems we have in this competition this week. All right, the 10-minute startup timer is counting down for the Utah team. And so as soon as our judges make sure that everything is ready to go, they're going to start a 30-minute clock for University of Utah, also known as the U. Robot is moving, an indication that the 30-minute timer has begun. Looking at the students in the control room, they appear to be stick driving this robot right now. All right, students are now hands off. So they did stick drive the robot for just a few seconds, and then they activated some sort of autonomous routine, and it appeared to drive straight into that crater. The students laughed. They're having positive attitude, even though things are not going exactly the way they had hoped. Typing in on their computer, screen right now. And they are driving manually through the obstacle field. There are craters in this robot is in the excavation zone. Should be noted that there are craters and rocks in the excavation zone in addition to the obstacle zone. So we saw this pretty decent sized robot, one of its wheels go into a crater just then, but this robot has a lot of ground clearance and a lot of grip in its large wheels. Okay, they are autonomous again. Joystick down. It looks like they aborted. Did not do exactly what they were hoping, and so it looks like they aborted. They're talking to the judges. It's possible they're asking the judges for a ruling if they're allowed to start digging right there, I would presume. Oh, I know what happened. Their camera appeared to freeze. The camera that is supplied by Lunabotics had an issue, and so they had to pause for just a second to correct that situation. And now they are starting autonomy. This is autonomous. No hands on keyboards, no hands on joysticks. All right, this is continuing to be autonomous, and they aborted. So there's some fine tuning that the students are doing in real time, it looks like. But what we just saw there was an autonomous dig, transport, and deposit for the University of Utah. Okay, autonomous again. Didn't get a very big bite autonomously. The student who did such a great job manually driving this robot during their first attempt is a really, really impressive driver. Also appears to be controlling this robot, configuring it, and launching the autonomous. Oh, if it digs there, they just aborted because it dug in a spot that it's not allowed to dig. So the judge is likely going to tell them to dump that material. Yep, they just dumped it. And now they're driving manually right now at this instant. This is still manual. This is the kind of aggressive digging and driving that awarded Utah the unofficial top of the field of amount of material in the scoring position during their first run. But I don't think this team wants to do their second run manually. They're typing on their keyboards, and I believe the student is possibly going to set up the robot for another autonomous run. But not yet. This is still looks like manual driving. 23 minutes remain for University of Utah's second run. They're manually driving right now, getting a good amount of material into the scoring zone, and I suspect they will try some autonomy at some point again later to get those precious autonomy points that teams in this competition so desperately need in order to be competitive. I should mention, even though this team, this robot, during their first run did bring in the most material into the scoring zone, they used a lot of power, a lot of onboard robot power to do that. You can see how this robot, when they're manually driving it, they stick their bucket into the ground, and then those four wheels just drive as hard as they can to push that bucket into the soil. So this robot is very productive, especially when being driven manually. But when you divide by the amount of power used by the robots, that can make a real difference in the overall score. So this is one of the many trades that these teams all have to go through. This team is now looking at that rock over there with interest. Again, this is Utah. There's a crater right in that same area that this robot is trying to avoid, and it appears to be focusing on that rock. And it's powerful enough. It's picked it up. It's driving off with that rock. Amazing. Powerful robot. That is not a trivial, that is not a small rock. That is very impressive. You can very impressive for University of Utah. That rock, it gets added to the volume that this team is adding into the scoring zone. Just because it's not fine-grained particulate material doesn't mean that it isn't part of the volume that is used for scoring. It totally is part of that volume. And I would venture to say very few teams in these final 10 teams have the power and the capability to move, especially pick up and move a rock of that size. Very impressive robot. With just under the 20-minute remaining mark for University of Utah. These students have at least temporarily given up on the idea of autonomous digging and autonomous scoring. But that doesn't mean that they won't come back to it later once they've gotten a good amount of material into the scoring zone. mentioned this before, but I'll go ahead and say it again. It's pretty important. Even though this team brought the most material to the scoring zone during their first run, it does not appear that they were doing any of that work in their first run autonomously, at least not from what we could see. Only the judges know for sure. So even though they brought the most material, doesn't necessarily mean that they're in a place to win this event. The autonomy points are worth so much that it is almost technically score-wise impossible to win this competition without autonomy. So this team knows that. They've read the rules. So I suspect they are going to try some autonomy in order to have a chance of being competitive against the other teams that are using autonomy. It's possible, though, that these students are so happy with their robot and its productivity under manual control that this team may be super happy and super focused on just trying to beat themselves, just trying to bring more material into the scoring zone during their second attempt than they did during their first. It's a big scoop right there. And honestly, the student who's driving this robot is making so few mistakes. The student is so productive and just dead on with their commands. I would say the student has a lot of practice with this operation in order to get this sort of efficiency. You can see the teammates pointing to the screen. This is a spot, pointing out maybe spots to avoid or spots to focus on. There's one student doing the driving right now, but there's an entire team that is helping to make this robot successful in this second run. Looks like they're shifting a little bit to a slightly different dig spot. a little bit harder to get a good bite there in that new spot. I've mentioned before about how this this volcanic rock material that is crushed into fine particles has some unique physical properties. It sticks together once it's under a little bit of load from material above it, and the main reason it sticks together like that and provides you resistance to your digging is because the particles are jagged in shape. Another problem with particles that are small and jagged is that they can really do damage. We mentioned that the judges are in full protective equipment to keep these particles out of their eyes, keep them from breathing these particles. And their skin is covered too, because these can be a bit of a skin irritant. These particles can also do damage to your robot, at least to sensitive parts of your robot. Camera lenses, soft rubber seals like motor seals, over time will get damaged by these small and rough particles. Even your digging surfaces over time will wear in a way or at a rate that is surprisingly high. So in a 30-minute run, you might not notice a ton of wear, but robots that we're designing to send to the moon that might operate for months or possibly, best case, years, we really have to focus on material selection and possibly even component and subsystem swap out and full replacement of new components on site due to higher wear than would normally be seen here on Earth by a similar system. This Utah team has picked a new spot so that they're not just digging a giant hole in one location. I'm trying to spread out the work and keep from creating a big old hole that might potentially get the robot stuck in. 10.5 minutes remain. So much time. Still 1/3 of this run still available on the clock for these students and their robot. Another thing about deploying systems like this on the moon, not necessarily a problem for our event, but systems that are deployed on the moon are likely going to have sensitive optics. For example, telescopes or other cameras or instruments like that will have sensitive optics, and also solar panels. Got a little front heavy there. At such a big load, and they were also pointing downhill. That's not a good combination. Change their center of gravity, their center of mass, to the point where they tipped forward. But solar panels and other optics that might be sensitive and have like glass fronts that need to maintain the integrity of that glass and the cleanliness of that glass can be problematic on the moon, because our equipment, other equipment that we send to the moon, could create dust. For example, excavation equipment could create dust. We're trying not to, but it can be really hard not to, And once you get dust on a solar panel on the moon, you can't just take a rag and wipe it off because, as I mentioned earlier, these dust particles are very jagged. They can do damage to the surface of your solar panel or to the surface of some sensitive optical instrument. So the less dust we can create by all of our equipment that we plan on sending to the moon, the better off we'll be in the long term. And so that's partly why some of the scoring criteria, some of the things that these student teams are being scored on here this week is how are they designing their robot to keep dust from being lofted in the air, and how little dust they actually do loft in the air. University of Utah continues to be very productive with their manual operations. 6 minutes remain in their second run. This side view starts to show both the ditch that they're creating when they dig and the pile that they're creating when they deposit. As big as this pile looks on camera, it's actually bigger than that in person. Camera just does not do it justice. It does become a little hard to dig when you've created a V-shaped trench. So the robot is starting on the downhill. Now the robot's facing down pretty sharply. And they're starting there and actually digging on the downhill side. Getting a little bit of a bite, but continuing that bite up the uphill side is a challenge because your chassis is changing from downhill to uphill, and compensating for that in real time is not easy. We are under 4 minutes in this second and final run for University of Utah. So it appears that the Utah team is not going to try for any autonomy points, but giving themselves a run for their money by potentially beating the amount of material scored in their first run, which was top of the field. They brought more material in their first run than any of the other teams in these finals. They appear to be trying to beat themselves and bring more material in their second run than they did in their first. Two and a half minutes remain for Utah. This driver has hit the mark in the scoring zone. Little, if any, material has been accidentally dumped outside the scoring zone. And there's been very little wasted excavation attempts by this student. So, kudos to the driver of Utah. Very impressive. Minute and a half remaining. This team is digging pretty deep now at the bottom of that V-shaped ditch that they've created. And so this material is getting a little bit tougher as they get deeper. But this robot has enough power, especially if it keeps all four wheels on the ground. "45 seconds left for Utah." By the way, the students are using the overhead camera that we are supplying, taking a point hit for using that camera. I wonder if by using that camera, they're unable to see the V-shaped. Let's give Utah a big round of applause. Two really amazing runs this year in Lunabotics finals. Great job, Utah. You should be proud of what you've accomplished. Great robot. Coming up next, we will see Colorado School of Mines enter the arena with their robot and compete for this year's grand prize here along with the other 9 other teams here at NASA's Lunabotics Finals 2025. Don't go anywhere. Colorado School of Mines coming up next.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
Go. Prop, go. CD8, go. Fido, go. All right, folks, go for launch.
Our destiny is always to go and see what's further and what's next.
Fido, nominal flight. Copy.
You're seeing the University of Utah students seeing their the amount of material, the volume of material that they have brought into the scoring zone. I had mentioned that they were maybe trying to beat themselves in their second run. They did beat themselves by nearly 30%. So their second run was really, really impressive amount of material brought into the scoring zone. So congrats to the University of Utah team. They beat themselves. We did not see any autonomy, sadly, but that the students are still really happy with what they were able to accomplish. this year. In the arena, we have the next team, Colorado School of Mines, getting ready for their second run. They've got 6 minutes remaining in their 10-minute startup time. And during that startup time, the student teams are setting up all their equipment in the mission control room that is required to monitor and control their robot. I just saw the robot's digging system move up and down, so they're testing commands to the robot right now during their setup time, and verifying that all the data is working and all the commands are working. Then, at the end of this 10-minute setup time, students will basically have 30 minutes to perform the task of getting through the obstacle field and excavating and delivering as much material as they can deliver in 30 minutes. Spicy in. Getting a close-up view of the Colorado robot. I just noticed there's some gold autographs, some gold signatures around this robot from presumably the students that have designed and created this robot. I don't see an abundance of cameras on this robot or other autonomy sensors. But this team wouldn't be here in the top 10 of the entire field if they hadn't had great success. Colorado School of Mines is Team Moon Pie. Their school is located in Golden, Colorado, which is between Denver and the mountains. As our setup clock winds down, we should see students in the arena leaving our arena, leaving only the judges behind. And the robot too, obviously. Once the students have left the arena judges will put the finishing touches, final looks on the arena, perform a radio call out that the arena is ready. The mission control judges will perform final looks in the mission control room, make sure those students are ready. They'll call out on the radio, mission control is ready, and then our timing judge will start the official clock. 30 minutes is the length of time that each student team has to perform their official competition runs. During those 30 minutes, teams will traverse an obstacle area that includes rocks and craters. They will dig or excavate in our excavation zone, and they will transport material that they have excavated into a scoring zone or scoring area, simulating a construction operation on the moon. Again, judges will not start the 30-minute run until everything has been checked and verified. All right, we're finally seeing movement from the robot, which means our 30-minute competition run has begun for Colorado School of Mines. All right, the Colorado School of Mines robot has made it into the excavation area, the digging area. They're allowed to dig anywhere in this corner of the arena, inside the chalk lines that are drawn on the ground. The students are most definitely using one of our supplied cameras, a pan tilt zoom camera that they control, that can give them kind of a overhead but diagonal view of their robot. There is a significant size crater there. There's two of them, one behind the robot and one in front and to the right. Right there, that's the first crater. That rear wheel just fell into it. So this robot doesn't have steerable wheels. It's a skid steer robot. So in order to turn to the right, the robot's left wheels, both of them, need to go forward, and the robot's right wheels, both of them, need to go backwards. Or maybe just stay still. You can see a rock to the right of the robot right now. You can see this robot flexing a little bit when it's trying to turn. Those wheels are digging in. Sorry, my camera work needs some work. These wheels are digging in a little bit instead of sliding across the surface. A skid steer robot like this needs to slide its wheels across the surface without resisting that turning. But they are now digging. You can see material being thrown into their onboard hopper. With 26 minutes remaining, Colorado School of Mines is now digging. Now they've backed up to the scoring zone. Didn't really see a lot of material come out. Now it looks like they're going back to digging. Oh, some material just came out of their onboard hopper just then. Sadly, not in the scoring zone. Okay, they just dumped out some more. I'm not sure the students, yeah, their camera view can see that. So they definitely saw the robot dump out some material in the excavation zone instead of in the scoring zone. Now they're plunging their digging system down again. We've got one student controlling their pan tilt zoom camera. We've got one student driving with a joystick and two students giving real-time feedback and encouragement and looking at data. It takes a team to compete in an event like this. This robot is so fast when it drives. I have trouble keeping up with it. All right, let's see if they're able to offload some scoring material this time. Yep, there they go. All right, Colorado Schools is off to a good start. You can see the trench that they left behind. If I can control this camera a little better. You can see their tracks on the right and left, and you can see the trench that they dug in the middle of their tracks right there. So, good productive work there by this Colorado School of Mines robot. Now they have backed up and they're digging closer to the scoring area, but still digging in the digging zone. I'm sorry, I'm just going to zoom out because I cannot follow. This robot is so fast. It runs back and forth faster than the camera can pan. Coming back to place some more material into the scoring zone. So far they've basically driven back and forth on the same tracks. Let's see how long that system works for them. At some point they will get deeper, and they will create a deeper and deeper trench in the middle in between their two rover tracks. At some point, they will reach the depth that their digger is unable to go any deeper, and they'll have to probably pick a new runway to drive on and dig on. And this is part of the planning process for us operating on the moon. We'll have to plan out all of our operations. I completely missed. I don't think they just dumped. They're just coming back to take another pass. Although it is possible, it was so fast that I missed it. Oh, I just realized something. Earlier when they dumped their load in the construction zone, in the excavation zone, which is outside of scoring, There is a chance that a mission control judge told them to do that because it does look like there's a little strip of the digging trench that is outside of the excavation zone. So if the judge witnessed that robot digging outside of the legal zone, that judge would have obviously told the team they're not allowed to drop that in the scoring zone. Could explain what we saw earlier. If this robot creates a trench that isn't super deep, then if the robot shifts to the right or left and one side of the robot, one set of wheels actually starts driving in that trench, as long as that trench isn't super deep, it's not really going to be a problem. And that may be what this team is doing. Their left wheels are essentially driving in the trench that they had dug earlier. And that may be completely on purpose. All of these robots have a limited amount of space that they're allowed to dig in. And some robots don't use very much space, and they just go super deep. Some robots use more space, and they go a little more shallow. So many trade-offs that these teams have in front of them when they're designing their robot at the beginning of the school year. This is Colorado School of Mines' second of 2 scoring runs for Lunabotics finals. Making a good trench right there. You can see the trench behind the robot. Looks like they got a little bit bound up, and so they raised their digger in the middle of that run, but then set it back down. Looks like they're going back for another pass because they have not shut down their digger. Yep, they're plunging their digger back down. They have to plunge it down enough to collect some of this simulated lunar soil, but not too far. If they plunge it down too far, it's just not going to have enough power, and it's going to bind up. So they have to fine-tune, all of the teams here have to fine-tune their systems. Looks like it just bound up there. They lifted it up, and it freed up again. Not only is your digger likely to bind up if you try and push too hard, but your wheels are likely to either bind up, or if they have enough power, they could start slipping and just sliding over the soil instead of getting a good grip on it, potentially loosening up the soil and causing problems later. So this competition is not easy for any of these teams. This is a 4-wheel drive robot. Most of our robots are 4-wheel drive or 6-wheel drive. You basically, it's pretty important to drive all of your wheels of your robot when driving on this this tough material. It's light and fluffy on top and pretty tough underneath. But occasionally we will see some of the wheels of this robot spinning and some of them not. And that is a case of non-productive work when you see that happen. Wasted energy. I think we're seeing that happen when this robot turns. Occasionally we'll see the two wheels on two opposite corners spinning and the two wheels on the other opposite corners not. And that's probably not what the students intend to be happening, because that's not very productive. This robot does appear to have a little bit of a problem turning. A lot of times when we've seen this robot try to turn, one of the wheels, front or back, depending on which is trying to push against the soil, kind of digs in instead of sliding over it. So that is something about the design here is making it a little bit hard for this robot to turn in place. Now we're back to some productive digging with 13 minutes remaining in Colorado School of Mines' second attempt. Now they did turn the robot a little bit, so it's no longer perpendicular to the scoring zone. So hopefully they'll be able to get the robot into the scoring zone without too much trouble, even though it's not perfectly facing in the right direction. Looking ahead, when this Colorado School of Mines run ends, do not go anywhere, because we're going to have a mini award presentation at the end of this run. So don't disappear, because you don't want to miss the award presentation. Ten and a half minutes remain in Colorado School of Mines' second run. Look at the pile they have deposited into the scoring zone directly behind the robot. And look at the trench being revealed behind the robot right now. Very productive work right now for this robot. This camera gives us a really close view of the offloading, the depositing of the material that has been collected. Wasn't actually a lot collected during that cycle. Still 8.5 minutes remaining, though. You can actually see material through the clear plastic. You can see material rolling over the top of their digging chain and falling into their onboard hopper. Their onboard hopper is a conveyor belt that will rotate slowly in order to make room for the material that's being tossed on board by their digging arm. Six and a half minutes remain for Colorado School of Mines. And you can see the piles of material that they have been able to successfully deliver into the scoring zone. After this run, we are going to have an award ceremony, and we will present the NASA Survey Granular Mechanics Award. And we are also going to give out the Artemis Educator Award. Again, coming up after this run, we will be giving out the NASA Survey Granular Mechanics Award and the Artemis Educator Award. So, don't run off at the end of this run. When this run is over, make your way down to the award ceremony end of the room for our little mini middle of the day award ceremony. 5 minutes remaining for Colorado School of Mines. Colorado is now has 2 minutes remaining in their run. It's been a minute since we've seen their robot move, though. The students are not panicking in the mission control room. I think they're happy with the outcome. They are zooming their camera into the side of the robot that has all the electronics, possibly looking at for lights, indications of things that are on. Basically troubleshooting why they are not able to control their robot anymore. Something must have happened. 50 seconds remaining. This is a tough environment for robots. So it's actually not uncommon for things to break. Either mechanical things or electronic things that are maybe sensitive to vibrations or shock. As time winds down for Colorado School of Mines, the students are smiling, laughing. The students are happy. Let's give Colorado School of Mines a big round of applause for their efforts and for the outcome of both of their runs. Good job, Colorado. Now, momentarily, over here by the stage, we are going to have a mini awards presentation. We're going to give out the NASA Survey Granular Mechanics Award, and we're going to give the Artemis Educator Award. So please make your way down to this end of the room, all of those in the building, and stand by for a mini award ceremony momentarily. For those online, we will be broadcasting this award ceremony, so don't go anywhere. And you are watching NASA's Lunabotics 2025 Finals event, broadcasting live from NASA's Kennedy Space Center Visitor Complex here in sunny and beautiful Central Florida. Hello. Is everybody having fun? It's day 3. You've made it to day 3. During today's little mini award ceremony at lunchtime, we're going to first give out the NASA Survey Granular Mechanics Award. And this award is going to be presented to you by Jared Long Fox, the UCF Planetary Exploration Research Scientist, representing NASA's Survey Center for Lunar and Asteroid Surface Science at the University of Central Florida. Jared Long Fox, come on up.
Hi, everyone. Thank you for the introduction, Kurt. Like he said, my name is Jared Longfox. I'm with the UCF Center for Lunar and Asteroid Surface Science, or CLASS. We are a node of NASA's Solar System Exploration Research Virtual Institute, or SERVI. Now that the alphabet soup's out of the way, I want to say it's my absolute honor to be here with you all at the Lunabotics competition this year. This competition is an amazing showcase of bold ideas and hands-on engineering innovations that are the hallmark of every NASA endeavor. Specifically, I am here to present the NASA Survey Granular Mechanics Award. This award recognizes a team that excelled in innovation in one of the most deceptively simple yet technically challenging aspects of planetary surface exploration, granular mechanics. Now, as you have all learned, if you didn't know before, through this competition, the lunar regolith and its simulants are incredibly difficult to work with. The dust gets everywhere, they're extremely abrasive, it poses hazards to electromechanical systems, and it has really different mechanical properties than anything we deal with here on Earth. Everything about this environment is alien and foreign to us. However, those challenges that the regolith presents are offset by its benefits. The regolith is our greatest resource on the moon. We can build with it. We can extract metals and oxygen from it. We can shield ourselves from radiation with it. We can set up entire lunar bases and live sustainably on the lunar surface using the regolith. And this award recognizes a team that has shown exceptional creativity and consideration in their engineering designs and insight in addressing these challenges. Because solving the granular mechanics puzzle is not just to improve our machines. It's to enable us to have a safe, sustainable, and efficient presence on the lunar surface for the rest of humanity's future. And now, it is my greatest pleasure to present the 2025 NASA Survey Granular Mechanics Award to the University of Virginia. Congratulations, team. Come on up. Someone take this. It's not mine. Right. You guys got it. Great. Okay, all set up. Yep.
Congratulations, Virginia. Well deserved. All right. Now we are going to present the Artemis Educator Award. The Artemis Educator Award is given to educators or facility or mentors in each challenge as nominated by student team members. Student team members recognize their faculty and mentors who inspire learners and motivate them to work hard, achieving more than the team members thought was possible. The award acknowledges the time and the dedication that the educators, faculty, and mentors take to be exceptional teachers. Educators, faculty, and mentors are noted for their commitment to learning and their valuable efforts for motivating and inspiring others. So, am I supposed to announce the... Bethany, am I supposed to announce the... All right, the team member... What am I supposed to say? Sorry. Which one is the lead? Okay. It's obvious now that she pointed it out to me. Great job. My bad. So, we're going to give 2 Artemis Educator Awards out today. The first one is going to be presented by the College of DuPage team lead, Naomi Daklush. Please come up, Naomi.
Hello, I'm very honored to present this award to our advisor, Dr. Eric Meloche. Not only is he the advisor at College of DuPage, but a lot of us had him for our classes, and he's just a great person. He really pushes us to perform our best, which is reflected this year. We reached achievements that we never even imagined. So thank you very much.
That is awesome. I should mention that what these educators and faculty and mentors are receiving for this award is a flag that was actually flown in space on the Artemis 1 mission. So this is an amazing award. It's not just a paper certificate. It's a real amazing relic flown in space. All right, our second Artemis Education Award flag, Artemis Phone flag, is going to be presented by Colorado School of Mining team lead Zachary Adams. Come on up, Zachary.
I'm not actually Zach. We just wrapped up our run, so we're still figuring some stuff out. But I am incredibly honored to give our professor, or our faculty advisor, Professor Jennifer Erickson, this award. Right now, she's actually at home due to an emergency, so she wasn't able to join us today. But I will give for some context, our team last year, we placed about 21st in the systems engineering paper, and this year's team is a brand new team, and none of us had any experience with systems engineering. And Professor Erickson gave us a lot of knowledge on where to start learning systems engineering, and gave us the resources to learn, to practice, to fail, and to learn, and just to grow. So incredible, incredible work. We love her so much, and she has gotten us to where we are today. We would not be here without her. So again, huge thank you to her.
She's watching.
Oh yes,
the
there we are.
Show her the camera what you got her.
And she's watching the stream right now. So here we are. It's for you. Awesome. Thank you so much.
All right, that concludes our mini award ceremony. Now go eat lunch if you haven't already, and don't miss the next competition. I wish I could remember who was coming up next. Help me remember. Help me. Purdue is coming up next. So don't go anywhere. You're watching NASA's Lunabotics 2025 Finals. See ya soon. Don't go far.
Station, not only from a technological perspective, but from a human side as well. The ISS is a marvelous technological platform for science. But what we have learned as an international community, crossing cultural differences, political differences, to support the men and women who are willing to go into space for exploration and science on behalf of all humankind, I think is one of the legacies that we're going to have. When you go outside at sunset or early in the morning and you track the ISS coming over your locale, realizing there are human heartbeats on board going at 5 miles per second. It's very special to realize that they are our friends, their families are important to us, and we do everything we can to maintain all the best of their health and well-being.
I get to help the astronauts launch and return from the International Space Station. There's been a lot of learning happening over the last couple years, 25 years now. I wish that everyone would know that the space station is one of the biggest international collaborations that NASA has. I think it is the foundation and testbed of just humanity's effort in space. The first ever flown in space object I got to touch was from working on ISS. Advanced Plant Habitat did an amazing thing where they flew some patches for us on station and returned them for the team that worked on the Advanced Plant Habitat project. So as someone who grew up loving space and wanting to work at NASA for more or less my entire life, that was a pretty impressive memory and remains something that I hold very dear. Moving forward, I hope to see more experiments, more of the science that gives us perspective on the human body and the workings in a zero-gravity environment, which will allow us to understand a microgravity environment like the moon or on Mars.
It's the only place in the world that we can do microgravity research. Think about that. One place in the whole world. There are no chambers on Earth where we can replicate microgravity, just the space station. So we have to use that in order to figure out what we need to do for exploration. The first thing we learned is what we didn't know, right? The questions we needed to ask. Moving from shuttle to space station, going from short duration to long duration, we discovered many, many things that we didn't even know were risks of spaceflight. But we can use a space station as a space analog for other space destinations. So that's really where we're going to focus, is how do we get to the moon safely? How do we get to Mars safely? Space station will allow us to do that.
International partnering, international cooperation, engaging research, those three things to me are one of the most important things that the ISS has provided. When we embarked in processing the elements of the ISS, nobody knew how to do it. We kind of figured that out as we were going through it. One thing that everyone should know about the ISS is that it's a great platform to do research, and that we need that platform and future platforms to help us understand how we're ever going to be able to go even farther out into deep space.
In terms of what I want to see, I think the continued amazing science that the ISS provides, a little bit of what they have provided to humanity is going to pay big dividends down the road. The deep space explorers that go beyond low Earth orbit, they're going to take a lot of things from the ISS. The ability to do things autonomously by themselves without the ground helping them is going to be one of the key things that the ISS provides them. The one thing that I hope people realize about the International Space Station is that it is not just America's, that it's humanity's. We're not just doing things for the benefit of the United States. It's just bigger than what we are.
Every new day for us now is a record until you come home. Thanks for that.
The space station is a platform for bigger and more complicated exploration. The greatest achievement of the space station is collaboration. To work together, countries come together, and once we are on board of the space station, living there in the case of the astronauts, we are all the same. It belongs to humankind. It belongs to all the nations that have collaborated and built this station, and furthermore, it belongs to all humans because of what we are researching and discovering for a better life on Earth.
I wish everyone knew that the space station is just a technological marvel designed by engineers all over the world. I think the ISS has a lot to offer for deep space explorers. It's helping us learn how to design and operate systems to keep humans alive. One day that stands out to me is when we launched Crew 1. I was the mission manager for that mission, and it was just an incredible achievement to finally be providing crew transportation services to ISS, which is the whole reason that Commercial Crew Program exists. I think the most important thing we've learned through the ISS program is the great things that we can achieve as really a human species if we work together.
Happy 25 years to the International Space Station.
Happy birthday, ISS.
Happy 25 years, International Space Station.
Happy 25th, ISS.
Happy 25 years, International Space Station.
Happy 25 years, International Space Station.
Happy 25 years to the International Space Station.
Happy 25th, ISS.
Happy 25 years, International Space Station.
Happy 25th birthday, International Space Station.
Happy 25th anniversary, ISS.
Happy 25th anniversary, ISS.
Happy 25 years, International Space Station.
Happy 25 years, International Space Station.
Happy 25 years, International Space Station.
We can't wait to see what's next for the space station.
NASA is preparing for a journey back to the moon, and after that, we're setting our sights on Mars. To get there, we need tons of rocket power coming from our Space Launch System.
When it comes to how much power this thing can push out, this thing is massive.
It's going to be mesmerizing to stand next to this massive vehicle. The immensity of it, knowing that this thing is going to be propelling a rocket into space and around the moon.
Hang on, it's probably best to start back at the beginning. It all started in Promontory, Utah, where Northrop Grumman manufactured each of the segments that make up the rocket's boosters. After a 10-day cross-country journey, the booster segments were delivered to Kennedy Space Center's Rotation, Processing, and Surge Facility, or RPSF. If this all sounds familiar, that's because it's the same facility that was used to process shuttle booster segments, which all came from Utah. Then they're ready to go to the iconic Vehicle Assembly Building, or VAB, where the rest of the motor segments are assembled and stacked on top of the mobile launcher.
So the one thing about this vehicle, of course, it's produced all across the country. Components all come here. They may be built around the country, but they all come together right here in the Vehicle Assembly Building.
Our SLS rocket will generate 8.8 million pounds of thrust to break through Earth's gravitational pull. That's more power than the Space Shuttle and the Saturn V rocket used. Teams with NASA's Exploration Ground Systems are responsible for assembling the boosters that will house the majority of that power. The twin solid rocket boosters, made up of 10 total motor segments, will stand nearly 17 stories when fully stacked. First, teams will inspect and prep the hardware. Next, they're ready to start stacking the segments, a process that takes time, patience, and a steady hand.
Once we have everything done in High Bay 4, we pick up the segment with a 325 crane, pick it up over the 16th floor crossover to where you see it now, and we begin stacking the segments. Each segment, we lift over the 16th floor crossover and stack it. Once we stack it, we put it on top of the segment below, and we put about 177 pins all the way around the whole thing to attach each segment.
And the pressure to perform the operation flawlessly can test the team's nerves.
There's a tremendous responsibility involved with processing flight hardware like this. It's nerve-wracking at times, but it's exciting. There's zero appetite for risk in a program like this.
We have a bunch of shuttle guys that are here to show us along the way. You know, if we get stuck, they're there to guide us. At the beginning of the stacking, it was very nerve-wracking. You know, with each segment that we stacked, a little bit of the nerve comes off. By the third or fourth one, it's easy peasy. You know, we're pushing through, all the jitters are gone, and we're just excited to get finished with it.
With all 10 booster segments now fully stacked on the mobile launcher, there's just one final piece of the puzzle to round out the power needed to get SLS off the ground and send it to space. Core stage. After a 900-mile journey aboard NASA's Pegasus barge, the SLS core stage, the largest rocket stage NASA has ever built, has made it to Kennedy Space Center.
Today is a huge day. This is the last piece of big hardware that we need for Artemis 1 processing. And we just
that looked at systems individually before culminating in pure power. With over 700,000 gallons of propellant flowing through the core stage and its RS-25 engines firing for 8 minutes straight, the successful final test resulted in some big emotions from the team.
We cried, we laughed, and we cheered because it was so emotional to see, you know, the years of culmination coming through.
And that victory did not come without overcoming a few challenges, proving why at NASA we test as frequently and as hard as we do.
And we got to shut down. All personnel.
So we actually did a 1-minute test on the first hot fire test. And then we learned a lot from that. We understood the vehicle more, we made a few changes, and then we got back into our second hot fire test.
There was a lot of joy and workmanship and ownership of being able to work that process and be able to get it done. When we went for the second hot fire and we went for 500 seconds, that was just pure exhilaration.
Following its arrival at Kennedy, teams moved the core stage into the VAB, where it was lifted by a crane and placed in between the twin solid rocket boosters. Serving as the backbone of the rocket, the core stage will provide more than 2 million pounds of thrust to help send the Orion spacecraft on its trip around the moon.
Essentially, we have these two massive cranes that are located inside of the BAB, where we go ahead and we pick 2 points at the end of the core stage, one on the back portion of it and on the front portion of it. We lift it up to the point where we're able to transition it from a horizontal position over into a vertical position, and then essentially bring it way up to the top of the vehicle assembly building and cross it over into high bay 3, in which we ensure that we don't damage any part of the vehicle as it's incoming into its position.
NASA's largest rocket stage, now fully integrated with the twin boosters, is ready to get Orion off the Earth. But it will take one more critical component to give the capsule that extra push it needs to journey tens of thousands of miles beyond the moon. With just a single RL-10 engine, the Interim Cryogenic Propulsion Stage, or ICPS, will provide over 20,000 pounds of thrust to send Orion on the ride of a lifetime. To connect the ICPS with the rocket stack, teams next added the launch vehicle stage adapter to the core stage, followed by the ICPS.
The ICPS is the Interim Cryogenic Propulsion Stage, and essentially it's somewhat of the upper stage of the entire SLS vehicle. And what that will do is propel the Orion capsule along with its service module over to its destination, which at this point in time will be the moon.
But before the spacecraft can be attached to the rocket, teams will conduct a series of tests to ensure all of SLS's components communicate properly with one another. plus the ground systems equipment, the launch control systems, and its software. Adding to the challenge, those methods for testing have changed significantly since the days of the Apollo program. Initially built in the 1960s to house assembly of the Saturn V, the VAB has undergone some major modifications to support several different kinds of rockets and spacecraft, whether they're going into low Earth orbit or venturing to deep space.
This high bay was Shuttle Heritage. Before that, it was Apollo Heritage. So there's upgrades that are still occurring today to include upgrades that will support Artemis II and Artemis III.
Rehearsal. The 322-foot tall, fully integrated rocket will roll out to Launch Pad 39B for a full test, allowing the launch team to run through a full launch countdown, but stopping just short of firing the engines.
I think we're going to be so proud when it rolls out of the VAB. I will personally be probably crying a little bit because it's such a big event and we worked so hard to get us to the day of rolling out. I'm probably going to be bawling when we launch it. See it through my tears because it's just a culmination of so much work from everybody.
We owe the advancement of science and research and technology to what we're doing here. And this is a big opportunity for us as a nation to reclaim our spot at the forefront of human space flight and exploration. Artemis is going to be a major part of history. It most definitely is going to rock the space industry when it flies. This program is going to go to the moon. It's going to go to Mars. We need that. This country needs that. This world needs that.
I'm so excited. It's going to be a lot of work ahead of us, but Artemis 1 is going to surprise everybody.
What an exciting day at the Kennedy Space Center. You can see the Orion spaceship coming out of the ONC building where we've been assembling it for several years. As big a step as this is for us today in rolling out and starting the journey of Artemis 1 to the moon and beyond, we're really excited for this test program to get this vehicle flowing and to begin the next steps, which are to send humans back to the moon.
The twin sister of Apollo, Artemis is the name given to the program that will return humanity to the moon. And named after one of the largest constellations in the sky, Orion is the spacecraft destined to get us there. Through Artemis missions, NASA will land the first woman and the first person of color on the lunar surface. And these missions will allow us to explore more of the moon than ever before, paving the way for long-term presence in lunar orbit.
We're rolling the Orion spacecraft out, but it's beginning its journey. We're really kind of at the end of the building process and the beginning of getting ready to go fly.
But before Orion can travel to our nearest celestial body, it must first make a few pit stops along the way to fuel up and get ready for flight.
As we leave here today, we're going to go to a facility that'll fuel the spacecraft with the rocket fuels and propellants it needs. We'll put a launch abort system on. We'll send it out to be stacked in the rocket and launched. And it's really the last few yards of the game.
Orion's journey to the moon began on the bayou. NASA's Michoud Assembly Facility in New Orleans is where technicians with Lockheed Martin began welding the pieces of the spacecraft's underlying aluminum structure together. 1 year later, it arrived in Florida, taking up semi-permanent residence inside the Neil Armstrong Operations and Checkout Building at NASA's Kennedy Space Center. Engineers and technicians will spend the next years working almost around the clock, outfitting Orion with thousands of components and pushing the capsule through several rounds of rigorous testing as teams prepare for its flight around the moon. The first step, though, is the crew module's arrival.
When the crew module shows up here at the ONC building, it's really just a welded shell of the structure. When it gets here, we put it into a fixture called the bird cage tool, and we use that fixture to position and attach all of the mechanically attached primary and secondary structure for the crew module.
Part of that includes the heat shield, which protects the crew module as it blazes through Earth's atmosphere at astonishing speed as it returns home. Technicians with Lockheed bond those thermal protection system products onto the heat shield right here in the ONC. And they do the same for the crew module's forward bay cover.
We bond that on here, and basically this covers the forward bay of the crew module such that once we come back into the atmosphere, this gets jettisoned and all of the landing system, i.e. parachutes, get deployed and slow the crew module down so that when it touches down in the ocean, it's only going a few miles an hour.
With the primary and secondary structures all attached, the crew module is tested to see how everything holds up. Orion is pressurized, stressing the welds to ensure they'll hold up under the proper loading. Afterwards, non-destructive evaluation of those welds is conducted to check for any voids or cracks. Once the structure is deemed strong enough, the crew module is moved just a few spaces down into the ONC's clean room for its next round of integrations.
We bring that structure into our clean room, which is you see behind me, because we need to start integrating the propulsion system and elements of the environmental control and life support subsystems, and those systems require a cleaner environment than the one we're standing in out here.
When all of that is done, the crew module is on the move again to the crew module integration station. There, all of the electrical systems, including wire harnesses and avionics boxes that control the crew module's guidance, navigation, communications, and its power subsystems, are integrated. Next, it's time to bring the spacecraft to life.
We power it up,
And then we go into a whole series of functional tests to make sure all the subsystems that we've integrated up to that point are functioning properly.
But the crew module isn't the only thing that makes up the Orion spacecraft.
All the people, the work, the components that have gone into this vehicle, it's just an amazing feat.
Teams also worked closely with the European Space Agency to build the service module, the element that will power Orion on its journey around the moon. Once that arrives, from Bremen, Germany, Lockheed moves forward with integrating the two.
The service module has a very similar life cycle to the crew module. We build it up structurally, we integrate the propulsion system and the other fluid systems, and then we integrate it electrically and power it up and do functional tests on it. And when we have a full service module and a full crew module, then we stack the two together and we have what's called the crew service module for Artemis 1.
Under the Artemis program, NASA plans to not only return to the moon, but to use that as a stepping stone to go farther than any human has ever gone before, Mars. To get there, it's truly a cross-country and international effort among thousands of individuals.
When you consider all the people, at the Johnson Space Center, Marshall Space Flight Center, all across the agency, SLS, Orion, the European Service Module, Boeing and their team, Lockheed Martin and their team, and to see all of that come together on that launch when we send it on its way to the moon, it's going to be absolutely amazing, and we're going to have a lot of really proud, happy people.
Building a spacecraft destined for deep space exploration from the ground up is no easy task. And the fact that these teams have been able to come together and do just that in the midst of a global pandemic is nothing short of amazing.
It really is a testament to the workforce. If you think about what we've been through over the years that they've been putting this together, and particularly think about the environment that this team was dealing with. We're dealing with COVID, and we're asking these folks to come into work every day and finish the spacecraft so we can keep this mission going. And we're ready, and we're excited. And so as they turn this over to us, we're ready to get going.
And really, this is only the start of Orion's path to the pad.
It's a little hard to put into words when you think about the fact that we are in the first flow of what will be our nation's deep space exploration program. It hits you in the heart, and it really speaks to why we all are doing what we're doing.
I never thought as a little kid growing up I'd be part of something like this today. Now as a dad of two young girls, to be able to tell them what I do and to be able to have them someday watch the first woman stand on the moon is pretty amazing to me personally.
As the Orion spacecraft departs the O&C, its next stop is the Multi-Payload Processing Facility, or MPPF, where teams with NASA's Exploration Ground Systems and prime contractor Jacobs will perform the next set of milestones, fueling and servicing the spacecraft.
We have a few months of hard but rewarding work ahead of us to get to launch, but this is it. This is our year. This is our time and what folks have worked so hard for.
Now, we're going to continue with processing, get that thing checked out, fueled, get the launch abort motor stuck on top of it.
With fueling of Orion's crew and service modules complete, the spacecraft moves from the MPPF into the Launch Abort System facility.
We just finished fueling the spaceship, and we moved it to the LASA facility, the Launch Abort System facility, to put the Launch Abort System on the top of Orion.
And in July 2019, teams completed a critical test, the Ascent Abort 2 flight test, to validate the Launch Abort System works as expected. After reaching an altitude of about 6 miles, where the test spacecraft experienced high-stress conditions expected during launch, the abort sequence triggered. Within milliseconds, the abort motor fired to pull the crew module away to safety. Its attitude control motor flipped the capsule into the proper orientation, and the jettison motor fired to release the crew module for a splashdown in the Atlantic Ocean.
I feel, just honored and humbled every day to be able to work on this.
This rocket is just going to be absolutely amazing.
Now that the spacecraft's launch abort system is securely in place, Orion is ready for the next stop on its path to the pad, the Vehicle Assembly Building. Once inside, the spacecraft will be placed on top of the Space Launch System rocket, the most powerful rocket the world has ever seen.
Across the nation are sacred sites that capture the spirit of America's character. And one of those places is right here, the Kennedy Space Center.
Every single vehicle that has carried humans beyond the bounds of low Earth orbit has undergone integration and testing in that Vehicle Assembly Building, crawled down this roadway and launched right here from the Kennedy Space Center. The Space Launch System, mated with the Orion spacecraft, will continue this proud tradition.
As soon as we roll out of the Vehicle Assembly Building, High Bay 3, and the world gets a chance to see this rocket, I think it is going to be shocking.
On March 17th, NASA took a giant step toward returning humanity to the moon. The fully assembled Space Launch System rocket and Orion spacecraft for the Artemis 1 mission made its debut outside the massive Vehicle Assembly Building.
We've seen the mobile launcher outside, and it's massive, but now add an over 300-foot rocket on top of it, it's just going to be amazing.
Charlie Blackwell Thompson oversees the launch countdown, ultimately providing the go for launch.
Entity, launch director, representing this team and all the men and women that have worked to make this day happen, I proudly give you a go to roll the Artemis launch vehicle to the pad.
Ladies and gentlemen, the world's most powerful rocket right here.
Once outside, the rocket began its nearly 4-mile journey to the pad, riding atop a 6.6 million pound crawler transporter, which was originally constructed to transport the Apollo moon rocket.
In 1 year, we have completely stacked the vehicle. We've completed most of our testing, all very successful, and we are so close to launch, and the excitement is just crazy.
Now NASA's new moon rocket is making the same journey the Saturn V took 50 years ago.
And just as all eyes are on the SLS tonight as it makes its journey, in a few short weeks, all eyes are going to be on the sky as it rocks the space coast and takes its maiden flight around the moon.
It is amazing to see the culmination of all of this work of many years from many industries and many people that have come and go, to have a chance to then now see their work going over to the pad and then launching to go to the moon.
The rocket is rolling to historic Launch Complex 39B, its launch pad used for both Apollo and shuttle launches, sending hundreds of astronauts to space throughout the decades, and now on tap to send hundreds more as we return to the moon and venture beyond to Mars. But for this mission, there will be no astronauts on board. Before the uncrewed Artemis 1 stack can launch to our nearest celestial body, it has to travel to the pad for a wet dress rehearsal, a test to run the rocket, capsule, launch team, and launch pad through their paces, simulating a launch countdown.
When we get to the pad team will be connecting all the interfaces between the pad and the mobile launcher so that we can go ahead and start our operations at the pad. So at that point, the launch director really takes over, and she will go down the sequence as if it was really a normal launch day.
Wet dress rehearsal is essentially launch without a launch. It is really the reason we're doing it is to verify and validate all of the pieces that go into launch countdown. So wet dress is really our opportunity to find any issues or adjustments that we need to make. and our launch countdown.
For Artemis 1, the wet dress rehearsal is the final and most critical test before the rocket can return to the launch pad for liftoff to the moon. During the countdown, over 730,000 gallons of supercooled liquid propellants will be loaded into the rocket as part of the nearly 2-day launch countdown.
We will configure all of the ground systems exactly the way we would for launch, and we will fully load the core stage and the interim cryopropulsion stage with their liquid fuels. That'll be the first time that that's been done from here at Kennedy Space Center. There have been pieces of these things done in multiple different areas. We've tested all of these systems in multiple different locations, but this will be the first time where we pull it all together into all of it, all in the same progression that we've got laid out for launch countdown.
Wet dress is the biggest milestone we have aside from launch, because that means that the rocket is now put together, has been tested separately and together, and it is ready to go and be filled with fuel to simulate how we're going to do it at the pad, and then it tells us the rocket is ready to go for launch.
And behind that wet dress rehearsal is a launch team made up of hundreds of engineers monitoring each system of the 320-foot-tall Artemis 1 rocket and capsule. Sitting in firing room 1 is the core launch control team, monitoring hundreds of launch commit criteria to ensure the ground systems and flight hardware are ready for launch.
Now you would think that launch control team in Firing Room 1 is it, that's all you need. We have an expansive support team across really the entire NASA enterprise that is supporting us on launch day.
And that support spans the entire nation, from additional systems engineers sitting in Kennedy's Firing Room 2, to the flight control team at Johnson Space Center in Houston, to the contractors responsible for designing and building each segment of the rocket and capsule.
This team is really shaping up to be a great, very skilled, and ready to operate and execute launch for Artemis 1.
With the Artemis 1 launch team now fully certified and the wet dress rehearsal complete, SLS and Orion are ready for their final pit stop, returning to the VAB before venturing back to Launch Pad 39B for liftoff.
I mean, we are going and we're going together, and we're having an opportunity to do this in a new generation of space exploration in which I can say that I'm honorably a part of.
You know, you come every day to the VAB and you see the rocket and you can't believe what we have accomplished.
People throughout history have always explored, and you never know what you're going to learn.
Exploration is not always about the destination, but it's the path that you travel, the things you learn along the way.
And the things we're going to learn are going to be incredible. We can't even begin to understand what those are today.
Our workforce has been a relentless spirit. We imagine, we build, we never stop pushing the envelope of what is possible. What President Kennedy said was, we choose to go to the moon and do other things, not because it's easy, but because it's hard.
The cost of failure is much higher than the cost of scrubbing. We have an obligation to get this right.
This is a whole new vehicle, a whole new technology, a whole new purpose of going back to the moon in preparation to go to Mars. And yes, it's hard.
The countdown to T-0 starts approximately 2 days before launch. Teams inside the Launch Control Center have been working around the clock, powering up each section of the rocket and configuring the launch pad to support the 8.8 million pounds of thrust our moon rocket will generate at liftoff.
It is a new creation. It is a new rocket and a new spacecraft to send humans to the moon on the very next flight.
Today, we make history. With the launch of the most powerful rocket the world has ever seen, we are taking the first step in humanity's return to the moon.
I can tell you there's an energy and there's an excitement around the Kennedy Space Center, I would say, across the agency and all around the Space Coast as we get closer and closer to this launch.
This mission will validate that the rocket and capsule do perform as expected before future Artemis missions send astronauts to the lunar surface.
We have worked really hard to get here. The team has done an absolutely outstanding job, and we're up to the challenge, and I'm really looking forward to a successful test flight.
You are looking at the world's most powerful rocket and Orion spacecraft live on Launch Pad 39B. Artemis 1 embodies the hard work of thousands across the world, determined to explore for the benefit of all. I'm Megan Cruz, and this is NASA astronaut Kayla Barron.
When I first walked up and saw the view from the desk here, I was just blown away.
This is the moment when it comes to the countdown, and then tension starts, and well, let's cross fingers, everything works well. Tension is rising, and we are fully excited here.
Over the past few years, teams have put in thousands of hours, performing simulations and rehearsals to ensure that they are ready for this moment.
As our 0 hour approaches for the Artemis generation, we do have a heightened sense of anticipation, and there's definitely excitement amongst the team members. We've noticed just the overall mood and focus within the team is definitely a positive one.
Now, with all systems configured correctly, the launch director gives the final go for liftoff.
On behalf of all the men and women across our great nation who have worked to bring this hardware together
to make this day possible. And for the Artemis generation, this is for you. At this time, I give you a go to resume count and launch Artemis 1.
This mission goes with a lot of hopes and dreams of a lot of people. It's no longer the Apollo generation. It's the Artemis generation. And that brings a whole new world of discoveries.
T-minus 50 seconds and counting. The Space Launch System is now counting down to liftoff of Orion on its maiden voyage to the moon. And here we go.
Okay.
Hydrogen burn-off igniters initiate. 7, 6, 5. 4-stage engine start. 3, 2, 1. And liftoff of Artemis 1. We rise together back to the moon and beyond.
Well, if you're just joining us, welcome to NASA's Kennedy Space Center, where we just watched Artemis 1 launch, our first step towards our next adventure into deep space.
With Orion off the ground, Mission Control in Houston takes the reins. Our nation is returning to the moon.
And we have worked hard as a team. You guys have worked hard as a team for this moment. This is your moment. It is not by chance that you are here today. So I want you to look around at this team and know that you have earned it. You have earned your place in the room. You have earned this moment. You have earned your place in history.
The successful launch of SLS is just the beginning. Orion will spend the next several weeks journeying around the moon, sending flight data back to teams here on Earth for real-time analysis. During its mission, Orion reached speeds traveling about 30 times as fast as the speed of sound.
This dramatic video of the Earth-Moon transit that took place showed and punctuated the fact that we were pressing away from our home planet to a distance of some 268,000 miles away from Earth, further than any human-rated spacecraft had ever traveled, for a spacecraft designed to return humans to Earth, eclipsing the mark set by the Apollo 13 vehicle back in 1970.
After several weeks of flight, it was time for Orion to return home.
A half-century later, NASA's newest moon explorer, the Orion spacecraft, is barreling its way back home after circumnavigating the moon and beyond in an elliptical distant retrograde orbit. Now less than 2 hours away from splashing down in the Pacific Ocean west of Baja, California, to complete its shakedown mission.
Like the Apollo missions of the past, Orion will have to endure incredibly high temperatures during re-entry of Earth's atmosphere.
A journey that began with the power of the launch of the Space Launch System 25 and a half days ago, about to reach its final minutes in the searing heat of re-entry, where temperatures around Orion will build up to 5,000 degrees Fahrenheit.
While re-entering Earth's atmosphere, the spacecraft slowed to about 300 miles per hour. As it continued its descent, Orion's parachute system, containing 11 total parachutes, deployed once it reached approximately 9,000 feet and a speed of about 130 miles per hour.
And there it is, high over the Pacific, America's new ticket to ride to the moon and beyond now in view. Orion under its chutes descending toward splashdown.
These parachutes help slow the crew module to a much more manageable speed, roughly 20 miles per hour, for a water landing off the coast of California.
Splashdown. From Tranquility Base to Taurus Littrow to the tranquil waters of the Pacific, the latest chapter of NASA's journey to the moon comes to a close. Orion, back on Earth.
We've got a perfect view, a front row seat to the Orion splashdown. And it's simply beautiful out here. That is a human-rated capsule that went around the moon and returned and is now in the Pacific Ocean.
I think I can speak for the whole dive team that we're honored to be part of history and to be part of something so monumentous, and just ready and excited to go out and do this.
When Orion was deemed safe to approach, team members jumped into the water and attached hardware that steadied the capsule.
What we do at NASA really is all about collaborations, and the collaborations that we've had with the Department of Defense in particular over the past many years, their hard work and their dedication as they went through a great deal of planning, hardware development and processes, and a lot of practicing to get to this point and make it look easy.
And that team, made of a combination of NASA and Department of Defense personnel, has put in years of work to make sure that they were ready.
Melissa Jones, the recovery director, just came from outside the ship's control center where she was monitoring and, of course, managing her team in the midst of this recovery. So, Melissa, thank you for being here.
Thank you for having me. It's just been a long time coming. We've been working this mission for a while, and we've done a ton of training. And every time you do training with a mock-up capsule, you don't have any of that. You don't have parachutes. You don't hear it coming back to the atmosphere, the sonic booms and all of that kind of stuff. And today that actually
You are watching NASA's Lunabotics 2025 Finals event, streaming live from NASA's Kennedy Space Center Visitor Complex. In the mission control room right now is the Purdue University team. Those students have just turned off NASA-supplied cameras, and they are going to be totally running from live data streaming from the robot. And there's a good chance that this Purdue team is going to be running this robot autonomously, completely hands-off from their controls. We're getting down to the final 30 seconds of their setup time. Once the setup time is complete, the students that helped put this robot into the arena will exit the arena, and the judges will start the event. The event being a 30-minute run for Purdue University, their second run of 2. This afternoon, we just returned from a lunch break. This afternoon, we are going to run Purdue, and then University of Illinois Chicago, and then University of Akron. That will complete 2 runs for all 10 of our finalist teams. And then, while the judges are verifying the scores, there is going to be a time period where we will take a break. I think we have a presentation during that time or a special award, but as soon as the judges can complete their formal verification of the scores, we will have our official award ceremony this evening, and we will be live streaming that award ceremony on our live broadcast here. Okay, we see the Purdue robot moving. Is the clock running? Looks like the clock is running. So this 30-minute run has started for Purdue. And the robot is very likely going to autonomously scan the area, looking for rocks and craters, so that it can autonomously traverse this obstacle field. This robot spins in place. It is a skid steer robot. 4-wheel drive skid steer robot. So to turn, it spins in place like a lot of our robots do. And now it has autonomously exited the starting gate. It is kind of traversing along the obstacle field. Looks like it is seeing those rocks. Oh, I didn't see that one. Spoke too soon. It's trying to drive over that rock. Now the students are either going to let it in order to maximize their opportunity for autonomy points, or they're going to step in and abort the potential of autonomy points in order to manually drive this robot. That rock was not a small rock. It looks like this robot is high-centered right now. That doesn't mean that it's impossible to get off of that rock, but it looks like right now the 2 of the wheels are touching the ground and 2 of the wheels appear to be in midair. The students are watching and they are not taking over control yet. There is some nervous energy though as this robot digs in a little deep. Both of these wheels on the right side of the robot are starting to dig down a little bit deep. Okay, the student has taken control of the joystick and aborted the autonomy. They gave it plenty of time to try and free itself, but sometimes if you haven't written software to specifically handle that situation, the odds of it automatically being able to fix and correct and get out of a sticky situation like that are not that great. So the students are lowering their digging implement, their bucket ladder system. That's going to push the front of the robot upwards and the rear of the robot down, possibly be able to make contact with the ground with the other wheels. The wheel in the upper right is starting to get buried pretty badly. It's actually turning in a little bit into a regolith digging implement, that wheel right now. This camera view is what the students are looking at in the control room, assuming that they have chosen to look at our cameras. So the student's actually unable to see, at least from our provided cameras, the other side of the robot that is actually digging itself a little bit deeper and a little bit deeper. There are cameras all over this robot though, so their onboard cameras may be able to see that other side of the robot and be able to see how deeply that side of the robot is digging itself in. The students cannot see this camera angle, but that is a very deeply buried wheel, and I'm afraid the rear one is maybe even deeper than that. Now if they push their digging implement into the ground, you can see that front wheel, which was buried just a second ago, is now up in midair. It's possible that this robot wheel will be able to push itself. That's as far down as that digging implement will go. Now they're running their digger backwards, so it's not actually digging. Just trying to provide some force in a direction to hopefully get unstuck from this rock that the autonomous system has gotten them on top of. It's obvious to us, because we can see all 4 wheels, that only the 2 wheels on the left just then were spinning. I'm not sure that if the students have that visibility. They should have data on their screens though that would show currents from each motor and that sort of highly technical, highly engineering quality data. There, all 4 wheels are running now. Purdue University had a really good first run with a lot of autonomy. And so far, this second run for Purdue has not been fun for these students. They appeared to be autonomously driving past the obstacle field up until the point where the robot turned and drove directly, not just into a rock, but over it, and now have high-centered the robot. The robot ended up with its all four wheels in the air, and that is kind of like a turtle on its back. For a robot, when you're high-centered, that is not a good place to be. There's a lot of wobbling, though. Every time they move those wheels around, the robot chassis wobbles, turns, moves. All this movement of the chassis on that rock could, over time, get it off-center just enough that it falls off of that rock just enough to get the wheel pressure on the ground that they're going to need to get out of this spot. This team is trying to push their digging implement as far down as it will go, but the robot is kind of upwards, so they're bottoming out on their depth of their digging system before it's actually getting to a spot where it can push their robot. Hate to see this happen. This team did have a really successful first run. They had a lot of that first run was running autonomously. So not only did they deliver a decent amount of material, but got some good autonomy points too for that first run. So even if this run ends up not getting any further than this rock, I believe these students have had some great experiences this year and had a really good first run that I'm sure they're happy with the results of that first run. The students are now thinking. They've put the joystick down and they're thinking and discussing like any good engineer does. All right. Looks like the students in the mission control room are packing up their computers. So sadly, this Purdue robot got stuck very early in its second run, and the students were unable to get it unstuck. So sad to see that happen for the Purdue students, although in the big picture they had a successful first run that they should be happy with. They've had all this great experience throughout this entire school year of designing and building and testing a lunar excavation robot, and coming to Florida to compete last week at UCF, and doing well enough in that competition that they were in the top 10, coming here to Kennedy Space Center Visitor Complex to compete in the finals. So let's give the Purdue University students a big round of applause for a great year and a great competition. Great job, Purdue. All right, the next team up on deck, we are down to our last two teams of this competition. We have University of Illinois Chicago on deck. After UIC, we're going to have University of Akron. So as our judges reset the arena, as our students remove this robot and put in the next, don't go anywhere, because you don't want to miss the last two runs of NASA's Lunabotics 2025 finals, streaming live from NASA's Kennedy Space Center. Don't go anywhere. UI Chicago and University of Akron are coming up next.
Did you know there's been over 1 million registrations in NASA's virtual guest program since May 2020? From your neighbor to the Crew 5 astronauts, you might be surprised who is a NASA virtual guest.
Do you have Mars 2020?
I do. Do you have James Webb?
Sure do. Do you have Crew 5?
Well, I've got it here, and you guys have it here, but I missed it here.
We conducted over 200 science experiments and technology demonstrations on our mission. We loved being part of Expedition 68. We even remembered a virtual guest passport for Einstein, our freefall indicator, but we forgot to register and missed the stamp.
Even if you're doing existing research, never miss a stamp from NASA's virtual guest program. Whether you're en route to the International Space Station or located anywhere around the globe. Register at nasa.gov/virtual guest to receive updates on missions and milestones. As a virtual guest, you will receive curated resources and a stamp for your passport following a successful launch.
Remember, you only get the updates and stamp if you register.
I joined. I won't miss it next time.
We are looking at the University of Illinois Chicago robot in the starting zone of the Artemis Arena, getting ready to start its second of 2 official runs in this competition this week. University of Illinois Chicago is second to the last run of our competition. After UIC, we're going to have the University of Akron as our final run. Then we will have a break, as short of a break as we can create, while giving our judges enough time to perform the verification of the scores. As soon as the judges have verified the scores, we will start an award presentation here on the stage end of the pit room. Right now, most of the teams have already finished both of their runs, and they are putting their robots away, putting their tools away, and relaxing. University of Illinois Chicago team is not relaxing yet, though. And neither is Akron, who will be coming up next. So the Chicago students are leaving the arena. Their 10-minute setup time is complete. Other UIC students are in the control room, and the run has begun. A 30-minute run for University of Illinois Chicago has started. Students appear to be stick driving this robot and driving this robot through the obstacle course. They went into a bit of a crater right there, but were able to get themselves out of it. They're almost to the excavation zone. They just have to get across that line before they start digging. The zone on the right of the line is the excavation zone. The zone on the left of the line is the obstacle zone. They just got through the obstacle zone and are starting a manual digging operation. This Colorado School of Mines had a good run earlier, their first run. They did not appear to do any autonomous operations, though, in their first run. They do have a unique digging system with a vibrating motor that vibrates their digging bucket while they drive their robot forwards during the dig process. And that vibratory motor spins up again for depositing the material into the scoring zone, because this material does not necessarily flow very easily. This simulated lunar regolith kind of sticks together almost like puzzle pieces. Not only does it resist your digging forces, it actually can resist dumping. So there you see the angle of their dump bed was angled up, but none came out until they activated their vibratory motor. And their vibratory motor kind of essentially fluidizes this particulate soil. All right, the students are hands off. So this is the start of their autonomy, it looks like. Let's see how. Okay, much less aggressive. That was very quick. But worth some major autonomy points, so the students are going to continue with this automated cycle. And I believe if they do it 3 times, they'll get another tier of points, of autonomy points. So that was 1 cycle. Students appear to be still hands off. So even if these 3 cycles of autonomous digging, transportation, and deposition, even if they don't end up depositing a lot of material, oh, they're hung up there. They just lost all the material they just dug, and the autonomous system does not realize it. Students are just letting it happen because there's, if they continue, nope, they just took over manual control. It looks like the dumping system was going beyond reason. There is a tier of autonomy points that the students do get by doing that 1 time. There's a better tier of autonomy points if the students are able to do that 3 times back to back to back, which is probably what they were going for just then. So the students have a decision now. They can just keep digging manually, or they can set their robot up for another autonomous cycle. There's a crater right there. Looks like they're straddling a good-sized crater right now. Okay, they're digging manually in this spot, which is, nope, they're autonomous. Student is not pressing any buttons on the joystick right now. Actually, I think they were pushing buttons on the joystick. It was just hard to see. Only the judge in the mission control center knows for sure. Yeah, the student is definitely stick driving the robot right now. So that dig was probably manual also. And look how full that hopper is. I'm not sure that hopper can hold any more than what's in there right now. Now the vibratory motor is not active yet. As soon as it activates, you'll see this stuff turn into a fluid state. Ooh. There you go. It also tends to make some dust. It almost bubbles and boils when it's being vibrated like this. Kind of crazy. It's still pretty thick when it's fluidized, you'll notice, almost like lava. That was a lot right there. I want to point out that this UI Chicago robot is much lighter than a lot of the robots in the field. Our maximum allowed robot mass for this competition is 80 kilograms. This particular robot weighed in at 53. So this team has designed a robot specifically to be much lighter than its competitors, but still be capable of doing the job. That could give them a scoring advantage when the material that they deliver to the scoring zone is divided by the mass of the robot. But here's the thing, the amount of material delivered into the scoring zone also gets divided by the power used by the robot. And I looked at the score sheet, and turns out this robot uses a lot of power. Uses more power than a lot of the other robots that it's competing with. So the lower weight and the more power may actually, at some level, cancel out a little bit. But a scoring advantage for having a lighter robot and a scoring disadvantage for using more power than your competitors can be completely overshadowed by whether or not you have any autonomy points in this challenge. And sadly, so far, I have not seen University of Illinois Chicago team do very much autonomy. They did appear to try earlier. That is digging down a very, very steep angle. Yeah, I think it just let loose. It was bound up on something. That steep of a digging angle is probably not going to work for long. Again, very, very steep digging angle. You can see the robot is not making forward progress. I think that digging angle is a little too steep right now. I just now noticed they have rubber grommets holding their hopper to their chassis. That way they can vibrate their hopper a lot without shaking the rest of the robot apart. You see those rubber That was a good load right there. 17 and a half minutes remain for University of Illinois Chicago. Plenty of time to bring a lot more material into the scoring zone. Earlier, I had mentioned that the University of Utah had brought the most material into the scoring zone during round one, during the first run of all 10 teams. Guess who was second? It was this team, University of Illinois Chicago, in the first round of 10 teams, brought the second most amount of material into the scoring zone. UIC is going to the far side of the excavation zone right now to do their excavation. I suspect as time goes on, they will start digging a little bit closer to the end point. Another really big load being deposited into the scoring zone. Going to get a really nice look at that vibratory action that loosens up the soil and allows it to fall out. You see it kind of bubbling and boiling, it looks like. Interesting physics going on there. Mechanics, I guess. Interesting mechanics. This team appears to be picking a different spot almost every time to dig in. They're making a pretty good-sized hole. The front wheels now, they were in midair. Most of the work is being done by the back wheels on this robot. Now it looks like all four wheels are being productive. As they change the angle, all four wheels end up making contact and helping push this robot. Students are not happy with that. They're going to go back for more. Vibrators turned on, pushing forward. Yeah, they're going to be happy with that right there. There is a little bit of binding going on in their bucket lift system that's causing them a little bit of issues here and there, where mechanisms are getting caught here and there. I could watch this all day. But there are only 12 and a half minutes in this run, so I'm only going to get to watch this for 12 and a half more minutes. The robot just found a little bit of a hole there. I think that's where it dug earlier. This robot's not afraid of holes by any means. It has enough mobility, enough ground clearance, enough power to fall into these pretty deep holes and still get itself out. Oh, one of their rubber grommets, I know that's not the right word. Their onboard bin lost one of its 4 attach points. You can see that rubber oval is busted. That may not be the end for this robot, though. It's a pretty tough little bot. With a bucket that full, though, it's really cantered sideways. From now on, the student team may decide to not fill their bucket up that full. All right, is this robot going to be able to dig efficiently with only 3 of its attach points remaining between the robot and its digging implement? Nine minutes remain in this 30-minute run for University of Illinois Chicago. They've made really, really productive use of their time. Let's see how well this thing digs with one of the attachment points missing. The students don't appear to be digging conservatively. They appear to be going for it. Looks like they got a pretty nice hopper full there. Not quite as full as their earlier ones, but still an impressive amount of material in a hopper that is partially detached from the robot, partially dangling. I am seeing some body language in the control room where the students are typing on their keyboard, possibly troubleshooting something. Now we're seeing a little bit of frustration in the body language in the control room. This robot hasn't moved in a minute. And they picked up the joystick again. And their vibration system appears to be working. Their lift mechanism appears to be working. I suspect that something had hung up or froze, and I suspect that the students restarted maybe something on board the robot. Just under 6 minutes remaining for University of Illinois Chicago. This side view shows kind of the low area where they've been digging a lot on the right, where the robot is right now. It also shows 3 really good sized piles of lunar simulant in the scoring zone. So this team has made a really nice sized berm on the moon to protect sensitive lunar equipment, for example. And this team did not give up when they noticed 1/4 of their attachment points between their digging bucket and their chassis had detached. They kept going, took a chance, and it has still been performing even with that issue. Appears to be sagging a little bit more over time and doing a little bit of binding, but so it is still operational. It may be limping a little bit, this robot, but it is still working hard. The little robot that could. Three and a half minutes left in this run. The final run for University of Illinois Chicago. Similar to Utah earlier, I wonder if University of Illinois Chicago is going to be able to actually beat their run 1 amount of material in the scoring position. If this team beats their earlier run, which was already second top of the entire field, while having a robot that is breaking down during its second run, that will be super impressive. Look how deep this robot is when it's digging. Hope it can get out of there. Unlike a lot of other robots in this competition, this robot doesn't have a lot of chassis to get hung up on, to get high centered on. There's wheels and a very minimal frame around the wheels and a very minimal frame around the digging bucket itself. So we've seen this robot just bury itself more than halfway up its wheels, and pop out of that spot without even blinking an eye. So maybe this is something that NASA might want to actually take under consideration when designing our lunar robots, to maybe minimize the chassis or rearrange the chassis and make a very, very minimal skeleton or frame, and basically wheels that could, worst case scenario, bury themselves and not have any trouble getting out of that situation. This is one of the benefits, one of the beautiful things about having a competition like this every year is we get so many prototype lunar robots of all different styles, all different engineering design decisions. Sometimes these students are thinking way outside the box from the way that the NASA engineers would otherwise think. And sometimes these students come up with some really cool new innovations. Just one of the many, many, many benefits of a competition like this. You're all seeing just the finals this week, but these students have been working on these robots for their entire school year. Did we lose the timer? Did I miss it? Are we done? All right, that's going to do it for University of Illinois Chicago. Let's give UIC a big round of applause for a job well done. This side camera view gives you a pretty decent shot of the amount of material this team has deposited into the scoring zone. It actually is bigger than it looks. Just hard to visualize with without good shadows and without any real contrasting colors. It's all just kind of gray. But the laser scan team is scanning this scoring zone right now, and hopefully we'll be able to pop that up on the screen and show you what it looks like later. So as the UIC team puts their computers and joysticks away in the Mission Control Center, and as they remove their robot from the arena, the University of Akron team is going to take their place in just a few minutes. So don't go anywhere. You don't want to miss the University of Akron coming up next at NASA's Lunabotics 2025 Finals event, streaming to you live this week from NASA's Kennedy Space Center Visitor Complex. Akron coming up next is the final team of the entire competition. You don't want to miss Akron coming up next. Don't go anywhere. You're watching NASA's Lunabotics 2025 finals competition. Right now, the University of Akron team, the Zips, are placing their robot inside our Artemis Arena. Artemis Arena is full of simulated lunar regolith, several feet deep. And all week long, we have had the top 10 teams from Lunabotics competition have come here to the Kennedy Space Center Visitor Complex to compete their robots in this arena. The object of the competition is to start in the starting zone, to traverse across an obstacle field, and to excavate or dig into inside the excavation area, and to transport and deposit material, excavated material, into the scoring zone. University of Akron is our final run of the day and our final run of this year's competition. They had a really good first run, this Akron team. And during their first run, they did have some autonomy. So be interesting to watch this team in their second run to see if they activate more autonomy than they did in their first run in order to try and grab some more of those precious, precious autonomy points. The Akron students are also getting ready in the mission control room. They've just arrived. You'll notice they're not setting up their computers yet. Students are allowed to set up their computers once a 10-minute setup timer begins. So stand by, don't go anywhere. We are about to run University of Akron in the final run of this competition. The Akron students are making good use of this downtime while they wait for the 10-minute setup clock to start. Just a heads up, at the end of this run, we will not immediately take a break. We will immediately have an award, a mini award ceremony. We are going to give out, immediately after this run from Akron, we are going to immediately give out, down here on the stage at the end of the room, we're going to immediately give out the Innovation Award. So Don't go anywhere. We will be streaming that Innovation Award live on this broadcast after this run. And then, after that, sometime later, after the judges have fully deliberated and fully verified the scores, then we will have our big final award ceremony. We will give out the Construction Award, the Autonomy Award, and the Grand Prize. We have purposely been spreading out our awards in order to focus just the final award ceremony on just the grand prize. This Akron team has 8 minutes left in their setup period. And we just saw the robot move, which indicates that the students in the control room have verified that commanding is working. The robot appears to have passed the wiggle test. You can see their excavation arm and bucket moving in this shot. So, wiggle test appears to have passed, giving the students full confidence that computers are working, networks are working, robot is working, everything is hooked up correctly. So with that, the Akron students in the arena are waving goodbye as they exit the arena, using only 3 minutes of their 10-minute setup period. This could be a really tense period for a team of college students who are about to compete in a major NASA robotics competition. These students are confident, they're having fun, they're smiling, laughing, dancing. They're confident in the work that they have performed throughout this entire school year to get to where they are today. And it looks like we are about to start the 30-minute run, the last run of this competition, right now. The robot is on the move. Our final run of this year's NASA Lunabotics competition has begun. Akron has left the starting zone. They're almost through the obstacle zone. And now they're in the excavation zone. This is where they're allowed to dig or excavate. I don't know if the students knew there was a big hole right there. That is on purpose. That is a crater that our arena judges have created, and this Akron robot appeared to not have any trouble getting out of that crater. This robot doesn't have as much ground clearance as a lot of other robots in the field, so we'll have to see if that affects their operation or not. Their wheels do have a lot of grip, though. You can see the design of their wheels have a lot of vertical ribs, treads. Looking at the students in the control room, it does appear that they're manually driving this robot, at least right now. They may try some autonomy later. The Akron robot appearing to line up for another dig pass. You can see they drive their wheels, trying to push that blade deeper into the soil. Now they're bringing the angle of the blade up. And I think they're happy with that. Yep, they've lifted it up. Now they're going to go deposit that into the scoring zone. You'll notice a white sphere mounted on the corner of their bucket. That is a 360-degree camera. They're not using it on board. It is recording to an SD card in 360 degrees, and so I'm looking forward to looking at that footage later. This Akron robot, the team is backing the robot back up to a spot where they can perform their next dig pass. They've pushed their bucket into the ground and they're driving their wheels. They're trying to maximize the amount of material in their bucket right now. And that's it. That's a full bucket for Akron. Nope, they're going for more. And I think they got more. I think they're satisfied with that amount of material in their bucket. We're only 5 minutes into this run. So if this team can take that efficiency, that productivity that we've seen over the last couple minutes and keep that up over the next 25 minutes, they will have a significant amount of material deposited into the scoring zone. The top few inches of this lunar Regulus simulant is light and fluffy, but once you get past the first couple inches, you get into the really hard-packed material, and If you're not prepared for that, if you haven't designed your robot for that, to handle that, it can be a little difficult. So as this robot digs deeper over time, we may see a difference in productivity. That does look like a good pile right there. That was a good spot to go for, I believe. This is University of Akron, 23 minutes to go in their 30-minute run. Their final run and our final run of this entire competition this year. This side view shows you the material that they've deposited from a better angle. It also shows you the digging zone that the robot is traversing through. That is a rough area right there, but it is very loose material right now because they haven't dug down very deep yet. That light fluffy material can be a little bit of an issue for some of these robots that don't have a lot of ground clearance. But this robot from Akron appears to be moving around just fine in that light fluffy material, thankfully. Akron team appears to be lining up for their next dig. Don't have much in the bucket this time. I'm trying to decide if that was autonomous, but I can't see the joystick right now. The judge in the mission control room knows for sure if that was autonomous because it's a requirement for the teams to notify the judge of such events. Yeah. That looks a lot like autonomous software. It's just a little bit off of how a human would drive a robot. All right, here comes another dig. Look how deeply they're digging right here. They're pushing, pushing, pushing. If I had to guess, that's the human driver. Just can't really tell from my video feed. They got a lot in the bucket that time. They got to be pleased with that. Coming into the scoring zone, once again, University of Akron, 19 minutes remaining. So 30-minute run, 1/3 through, 2/3 remaining. Plenty of time to continue to bring bucketfuls of this simulated lunar soil into the scoring zone. So there's a, okay. There's a rock there, but didn't cause any major problems. They got a pretty good bite that time. Pushing the bucket in at just the right angle. If you go too steep, you're going to go deep and bind up and just not be able to make progress. If you go too shallow, you're going to skip over the top and you're not going to get as much in your bucket as you had wanted. This team is having some very productive dig, transport, and dump cycles, though. The students in the control room are intently watching one of the monitors in front of them, which is the camera feed that we are providing that is emulating a camera on the lander. And the students are able to control the pan, tilt, and zoom of that camera. They do get a point penalty for using that camera, but a lot of teams will take that point penalty for the benefit of having such a view. This is the University of Akron Zips driving their robot in our Artemis Arena, pushing their blade into the soil, the simulated lunar soil, as far as they can until the robot doesn't move anymore, and then lifting their bucket up and depositing it into the scoring zone. Their wheels are getting pretty deep right now. I'm a little bit worried. The students appear to be pushing the bucket down. I was going to say to try and get their wheels out, but that does not appear to be what they just did just then. They may be able to pull that bucket or pull their wheels forward using the bucket. So what may be happening is the wheels were spinning in place because they were pushing too far into the soil, trying to get a bigger bite than the robot was capable, and got their wheels. There they got themselves out. Great job, Akron. That was a little scary there for a minute. All right, now let's get back to work with the digging, transporting, and delivering simulated lunar simulant into the scoring zone. What just happened is so easy to occur in this material. As I mentioned, the top couple inches are light and fluffy. Beneath that, it's fairly packed and quite hard. And so if you get your wheels spinning in the light fluffy stuff to the point where they sink down. If it goes far enough that your chassis ends up resting on this material and your wheels are just free spinning, that is not a good place to be for a lunar robot. This team, are they gonna pick that same track, or are they gonna find a different digging spot? That spot that they were just in is now even more light and fluffy than it was before, so could be risky. Right there, that's the spot they were just in, isn't it? You can see that rear wheel is just completely full of regular simulant. It's actually acting as a digging implement right now, that wheel. All these wheels are acting like digging implements. Yeah, they're almost exactly in the same spot as earlier. Let's hope they can get out of it again. 12.5 minutes remain. The fact that, if I zoom in here, the fact that the wheel is buried and the chassis is sitting on material is what is got them stuck right now. So if they can drag this robot forward inch by inch using their bucket, they'll be able to get this wheel out of that hole and into a high spot. It may take a while to just slowly, centimeter by centimeter, move this robot forward. I just now realized the spokes on this robot are wires. I love that. I don't know why I didn't notice that before. Okay, students are typing into their computer. They may be changing some settings, some current limits possibly, some speed, motor speed default parameters possibly. And they're still stuck, almost as if in quicksand. They're not going any deeper though, because the chassis of the robot is sitting on material that is tough enough to hold their weight. Students are still typing into the computers. Okay, here they go with the arm again. Maybe that arm can help get them out. You hate to see a team like this get stuck after being so productive and having such a great start. I will say, though, that this is a good learning situation for these students. They may be a little frustrated about the current situation right now, but in the long run, they are learning so much during this troubleshooting time. It's immeasurable how much they're learning in diagnosing the situation, thinking about what are the parameters that they can control, and trying different things. to try and alleviate the situation. The students are thinking about the situation. One of them is typing on their keyboard. So they haven't given up yet. As long as you see typing on the keyboards or pushing of buttons on a joystick, you know the team has not given up. They did put their joystick down, and we have a judge that has entered the arena, which is possibly an indication that this team has decided to call it. Yep, here come the Akron students into the arena. So, sad to see the robot get stuck, but before it got stuck, it was very productive, and the first run for this team was also very productive and successful. Let's give the University of Akron team a big round of applause for both of those runs this week in NASA's 2025 Lunabotics Finals. Great job, Akron. We're proud of you. Now, as I mentioned earlier, that was our last run. But if you disappear right now, you are going to miss a very important mini award ceremony. We are going to immediately give out the Innovation Award. So please make your way down to the stage area of the room, and we will present the Innovation Award momentarily to one of our deserving teams.
What an exciting day at the Kennedy Space Center. You can see the Orion spaceship coming out of the ONC building where we've been assembling it for several years. As big a step as this is for us today in rolling out and starting the journey of Artemis 1 to the moon and beyond, we're really excited for this test program to get this vehicle flowing and to begin the next steps, which are to send humans back to the moon.
The twin sister of Apollo, Artemis is the name given to the program that will return humanity to the moon. And named after one of the largest constellations in the sky, Orion is the spacecraft destined to get us there. Through Artemis missions, NASA will land the first woman and the first person of color on the lunar surface. And these missions will allow us to explore more of the moon than ever before, paving the way for long-term presence in lunar orbit.
We're rolling the Orion spacecraft out, but it's beginning its journey. We're really kind of at the end of the building process and the beginning of getting ready to go fly.
But before Orion can travel to our nearest celestial body, it must first make a few pit stops along the way to fuel up and get ready for flight.
As we leave here today, we're going to go to a facility that'll fuel the spacecraft with the rocket fuels and propellants it needs. We'll put a launch abort system on. We'll send it out to be stacked in the rocket and launched. And it's really the last few yards of the game.
Orion's journey to the moon began on the bayou. NASA's Michoud Assembly Facility in New Orleans is where technicians with Lockheed Martin began welding the pieces of the spacecraft's underlying aluminum structure together. 1 year later, it arrived in Florida, taking up semi-permanent residence inside the Neil Armstrong Operations and Checkout Building at NASA's Kennedy Space Center. Engineers and technicians will spend the next years working almost around the clock, outfitting Orion with thousands of components and pushing the capsule through several rounds of rigorous testing as teams prepare for its flight around the moon. The first step, though, is the crew module's arrival.
When the crew module shows up here at the ONC building, it's really just a welded shell of the structure. When it gets here, we put it into a fixture called the bird cage tool, and we use that fixture to position and attach all of the mechanically attached primary and secondary structure for the crew module.
Part of that includes the heat shield, which protects the crew module as it blazes through Earth's atmosphere at astonishing speed as it returns home. Technicians with Lockheed bond those thermal protection system products onto the heat shield right here in the ONC. And they do the same for the crew module's forward bay cover.
We bond that on here, and basically this covers the forward bay of the crew module, such that once we come back into the atmosphere, this gets jettisoned and all of the landing system, i.e. parachutes, get deployed and slow the crew module down so that when it touches down in the ocean, it's only going a few miles an hour.
With the primary and secondary structures all attached, the crew module is tested to see how everything holds up. Orion is pressurized, stressing the welds to ensure they'll hold up under the proper loading. Afterwards, non-destructive evaluation of those welds is conducted to check for any voids or cracks. Once the structure is deemed strong enough, the crew module is moved just a few spaces down into the ONC's clean room for its next round of integrations.
We bring that structure into our clean room, which is you see behind me, because we need to start integrating the propulsion system and elements of the environmental control and life support subsystems, and those systems require a cleaner environment than the one we're standing in out here.
When all of that is done, the crew module is on the move again to the crew module integration station. There, all of the electrical systems, including wire harnesses and avionics boxes that control the crew module's guidance, navigation, communications, and its power subsystems, are integrated. Next, it's time to bring the spacecraft to life.
We power it up,
And then we go into a whole series of functional tests to make sure all the subsystems that we've integrated up to that point are functioning properly.
But the crew module isn't the only thing that makes up the Orion spacecraft.
All the people, the work, the components that have gone into this vehicle, it's just an amazing feat.
Teams also worked closely with the European Space Agency to build the service module, the element that will power Orion on its journey around the moon. Once that arrives, from Bremen, Germany, Lockheed moves forward with integrating the two.
The service module has a very similar life cycle to the crew module. We build it up structurally, we integrate the propulsion system and the other fluid systems, and then we integrate it electrically and power it up and do functional tests on it. And when we have a full service module and a full crew module, then we stack the two together and we have what's called the crew service module for Artemis 1.
Under the Artemis program, NASA plans to not only return to the moon, but to use that as a stepping stone to go farther than any human has ever gone before, Mars. To get there, it's truly a cross-country and international effort among thousands of individuals.
When you consider all the people, at the Johnson Space Center, Marshall Space Flight Center, all across the agency, SLS, Orion, the European Service Module, Boeing and their team, Lockheed Martin and their team, and to see all of that come together on that launch when we send it on its way to the moon, it's going to be absolutely amazing, and we're going to have a lot of really proud, happy people.
Building a spacecraft destined for deep space exploration from the ground up is no easy task. And the fact that these teams have been able to come together and do just that in the midst of a global pandemic is nothing short of amazing.
It really is a testament to the workforce. If you think about what we've been through over the years that they've been putting this together, and particularly think about the environment that this team was dealing with. We're dealing with COVID, and we're asking these folks to come into work every day and finish the spacecraft so we can keep this mission going. And we're ready, and we're excited. And so as they turn this over to us, we're ready to get going.
And really, this is only the start of Orion's path to the pad.
It's a little hard to put into words when you think about the fact that we are in the first flow of what will be our nation's deep space exploration program. It hits you in the heart, and it really speaks to why we all are doing what we're doing.
I never thought as a little kid growing up I'd be part of something like this today. Now as a dad of two young girls, to be able to tell them what I do and to be able to have them someday watch the first woman stand on the moon is pretty amazing to me personally.
As the Orion spacecraft departs the O&C, its next stop is the Multi-Payload Processing Facility, or MPPF, where teams with NASA's Exploration Ground Systems and prime contractor Jacobs will perform the next set of milestones, fueling and servicing the spacecraft.
We have a few months of hard but rewarding work ahead of us to get to launch, but this is it. This is our year.
Hello, teams. Who's ready for the Innovation Award? I know, we're all tired. Who's really ready for the Innovation Award? Yeah. I get it, I'm tired too. Not as tired as y'all, because I was thinking, boy, this has been a long 3 days. You all have been doing this for how many days now without really any breaks? You started, what, Thursday of last week at UCF? So kudos to all of you students for persevering. All right, we are going to give away the Innovation Award. This is not the beginning of the final ceremony. The final ceremony needs a little bit more time for our judges to finalize the scores and have their final discussions, make sure they're all on the same page. So just the Innovation Award. It's a little mini award ceremony. We will dismiss after this and then come back soon after. So if you're going to leave, make sure you either keep an eye and ear on our live stream for announcements of how soon the final ceremony is going to happen, or just leave somebody in the room to monitor. Does that sound fair? Because do we have a guess as to how long it's going to take for the final award ceremony? Probably a half hour, so kind of keep that in mind. All right. I would like to introduce Rob Mueller, who's going to present the Innovation Award.
So thanks for all the good work. At the beginning, I said stay safe, have fun, and do good work. Everybody have 10 fingers? Okay, so you stayed safe. Did you have fun? Okay, and I know you did good work because I saw it, so congratulations. We talk about this competition in this award about, it's not about winning, it's about being innovative. And I had a chat with a few students earlier, and I said, you really aren't being innovative. What do you mean? It's like, we want you to push the box, push the boundaries. That's what this prize is all about. So I'm going to read the criteria. This award is given to teams that have the best. Hold on, I'm going to have to put my glasses on. It's terrible. This award is given to teams that create new, innovative ideas and solutions within the scope of their respective challenge. Ingenuity, creativity, and inventiveness in either technology or non-technology focused ideas are awarded for their original ideas, creating efficiency, effective results, and or solving a problem. Now what's really cool is that this year they came to us and they said, we have a special prize. It's a flag that was flown in space on the last Artemis mission, and we have 2 of them. So you have to pick 2 Innovation Prize winners because we have 2 flags. So I said, not a problem. We'll pick 2. This flag was flown aboard the Artemis 1 mission, which launched on November 16th, 2022, and splashed down on December 11th, 2022. This was the first uncrewed integrated mission of our new deep space exploration system, Orion, with its European-built service module launched atop the Space Launch System rocket from Launch Pad 39B here at NASA's Kennedy Space Center in Florida. The Artemis 1 mission tested the system's capabilities to orbit the moon and safely return to Earth. Orion traveled 19,908 miles further than the Apollo capsule, 43,051 miles beyond the moon, and 268,563 miles from Earth. So this is the first time we've been around the moon with this kind of a spacecraft since Apollo. So it's a big achievement. And we're giving away this flag to 2 teams that were very innovative. So I'll get right to it. The first team that was worthy of the Innovation Technology Award and will be given an Artemis flown flag is the University of Virginia for their bucket drum. don't you give it? Now, while he gives the award, the details are that they took a bucket drum.
Sorry.
They took a bucket drum and they made a big bucket drum, and then they raise and lower the bucket drum, which is really the secret of making it work, is having just the right bite size. But it was just different, and if you're innovative and different, that's what this prize is all about. So congratulations to your team. The second flag for the Innovation Technology Award is awarded to the University of Illinois in Chicago. It's not a first and a second. They're both equal. They both get the innovation prize because we have two flags that were flown in space. These are very special flags. So congratulations to you. Now, you may have noticed that last year they won the Innovation Award too with a similar design. So you may say, well, can you win innovation 2 years in a row? Well, then it's relative to the other teams, and they were still more innovative than most of the other teams. And if you saw the way that robot digs itself into the ground and then gets out again, it's pretty amazing. So congratulations to your team.
Thank you, Rob. And now we will dismiss, or you can just hang out. And we think it will take about a half an hour before we will start our final award ceremony of the competition. So don't go too far, and be checking in either here in the room or online for the start of our final award ceremony to begin very soon.
What President Kennedy said was, we choose to go to the moon and do other things, not because it's easy, but because it's hard.
The cost of failure is much higher than the cost of scrubbing. We have an obligation to get this right.
This is a whole new vehicle, a whole new technology, a whole new purpose of going back to the moon in preparation to go to Mars. And yes, it's hard.
The countdown to T-0 starts approximately 2 days before launch. Teams inside the Launch Control Center have been working around the clock, powering up each section of the rocket and configuring the launch pad to support the 8.8 million pounds of thrust our moon rocket will generate at liftoff.
It is a new creation. It is a new rocket and a new spacecraft to send humans to the moon on the very next flight.
Today, we make history. With the launch of the most powerful rocket the world has ever seen, we are taking the first step in humanity's return to the moon.
I can tell you there's an energy and there's an excitement around the Kennedy Space Center, I would say, across the agency and all around the Space Coast as we get closer and closer to this launch.
This mission will validate that the rocket and capsule do perform as expected before future Artemis missions send astronauts to the lunar surface.
We have worked really hard to get here. The team has done an absolutely outstanding job, and we're up to the challenge, and I'm really looking forward to a successful test flight.
You are looking at the world's most powerful rocket and Orion spacecraft live on Launch Pad 39B. Artemis 1 embodies the hard work of thousands across the world. determined to explore for the benefit of all. I'm Megan Cruz, and this is NASA astronaut Kayla Barron.
When I first walked up and saw the view from the desk here, I was just blown away.
This is the moment when it comes to the countdown, and then tension starts, and well, let's cross fingers, everything works well. Tension is rising, and we are fully excited here.
Over the past few years, teams have put in thousands of hours, performing simulations and rehearsals to ensure that they are ready for this moment.
As our 0 hour approaches for the Artemis generation, we do have a heightened sense of anticipation, and there's definitely excitement amongst the team members. We've noticed just the overall mood and focus within the team is definitely a positive one.
Now, with all systems configured correctly, the launch director gives the final go for liftoff.
On behalf of all the men and women across our great nation who have worked to bring this hardware together.
To make this day possible. And for the Artemis generation, this is for you. At this time, I give you a go to resume count and launch Artemis 1.
This mission goes with a lot of hopes and dreams of a lot of people. It's no longer the Apollo generation. It's the Artemis generation. That brings a whole new world of discoveries.
T-minus 50 seconds and counting. The Space Launch System is now counting down to liftoff of Orion on its maiden voyage to the moon. And here we go.
10.
Hydrogen burn-off igniters initiated. 7, 6, 5. 4-stage engine start. 3, 2, 1. And liftoff of Artemis 1. We rise together back to the moon and beyond.
Well, if you're just joining us, welcome to NASA's Kennedy Space Center, where we just watched Artemis 1 launch, our first step towards our next adventure into deep space.
With Orion off the ground, Mission Control in Houston takes the reins. Our nation is returning to the moon.
And we have worked hard as a team. You guys have worked hard as a team for this moment. This is your moment. It is not by chance that you are here today. So I want you to look around at this team and know that you have earned it. You have earned your place in the room. You've earned this moment. You have earned your place in history.
The successful launch of SLS is just the beginning. Orion will spend the next several weeks journeying around the moon, sending flight data back to teams here on Earth for real-time analysis. During its mission, Orion reached speeds traveling about 30 times as fast as the speed of sound.
This dramatic video of the Earth-Moon transit that took place showed and punctuated the fact that we were pressing away from our home planet to a distance of some 268,000 miles away from Earth, further than any human-rated spacecraft had ever traveled, for a spacecraft designed to return humans to Earth, eclipsing the mark set by the Apollo 13 vehicle back in 1970.
After several weeks of flight, it was time for Orion to return home.
A half-century later, NASA's newest moon explorer, the Orion spacecraft, is barreling its way back home after circumnavigating the moon and beyond in an elliptical distant retrograde orbit. Now less than 2 hours away from splashing down in the Pacific Ocean west of Baja, California, to complete its shakedown mission.
Like the Apollo missions of the past, Orion will have to endure incredibly high temperatures during re-entry of Earth's atmosphere.
A journey that began with the power of the launch of the Space Launch System 25 and a half days ago, about to reach its final minutes in the searing heat of re-entry, where temperatures around Orion will build up to 5,000 degrees Fahrenheit.
While re-entering Earth's atmosphere, the spacecraft slowed to about 300 miles per hour. As it continued its descent, Orion's parachute system, containing 11 total parachutes, deployed once it reached approximately 9,000 feet and a speed of about 130 miles per hour.
And there it is, high over the Pacific, America's new ticket to ride to the moon and beyond now in view. Orion under its chutes descending toward splashdown.
These parachutes help slow the crew module to a much more manageable speed, roughly 20 miles per hour, for a water landing off the coast of California.
Splashdown. From Tranquility Base to Taurus Littrow to the tranquil waters of the Pacific, the latest chapter of NASA's journey to the moon comes to a close. Orion, back on Earth.
We've got a perfect view, a front row seat to the Orion splashdown. And it's simply beautiful out here. That is a human-rated capsule that went around the moon and returned and is now in the Pacific Ocean.
I think I can speak for the whole dive team that we're honored to be part of history and to be part of something so monumentous, and just ready and excited to go out and do this.
When Orion was deemed safe to approach, team members jumped into the water and attached hardware that steadied the capsule.
What we do at NASA really is all about collaborations, and the collaborations that we've had with the Department of Defense in particular over the past many years, their hard work and their dedication as they went through a great deal of planning, hardware development and processes, and a lot of practicing to get to this point and make it look easy.
And that team, made of a combination of NASA and Department of Defense personnel, has put in years of work to make sure that they were ready.
Melissa Jones, the recovery director, just came from outside the ship's control center, where she was monitoring and, of course, managing her team in the midst of this recovery. So, Melissa, thank you for being here.
Thank you for having me. It's just been a long time coming. We've been working this mission for a while, and we've done a ton of training. And every time you do training with a mock-up capsule, you don't have any of that. You don't have parachutes. You don't, hear it coming back to the atmosphere, the sonic booms, and all of that kind of stuff. And today, that
Hello, Lunabotics teams and guests and staff and volunteers. Thank you for your patience. Thank you for waiting all the way till the end, the final awards ceremony of NASA's Lunabotics 2025 competition. Who is ready? Who is glad this competition's over? You all should be so proud for getting this far. I mean, your entire school year has culminated around these robots, and I'm so glad that you all have made it this far, gotten through the entire competition. Hopefully, regardless of the outcome, hopefully you all had a great time and had a great experience and have something really amazing to put on your resumes. Am I right? That's what I'm talking about. All right. Caterpillar is going to start off our ceremony by giving some special awards. Help me give a big hand to Eric Reiners, the Automation and Autonomy Lead at Caterpillar Tractor Company.
All right. This is my favorite part of the whole competition. So to start off our portion here with autonomy this evening, I'm going to introduce John DeSellum. If you go to the next slide, Chris. John DeSellum, who's our Vice President in Mining Autonomy at Caterpillar, and he's going to say a few words to you all tonight. So, John, if you want to come up.
So first of all, thank all of you. You know, it really reinvigorates me. I told a story earlier this week to some of the folks in this room. In 1997, you know, I was around your age and in my last year of college, and Caterpillar showed me a video of our first autonomous trucks, and they were pretty stupid at the time, but I saw that and I'm like, that's where I want to go work, and that's what I want to work on. And I've been very blessed in my life to be able to get to where I am and do those things, and I hope all of you get an opportunity to chase your dreams in the same way. And I hope that you look back on this time, and it's a time that not only was it hard and all that, but that you learned from it and you grew from it. And I think of you know, those of you that did very well. I'm sure there was lots of long nights that went into it, and those of you that maybe didn't perform like you thought you might, there's still learning that took place. There's still things that you grew with. And some of the greatest adventures in life feel like catastrophes while they're occurring. So remember that. But, you know, I really do want to say thank you. Again, it reinvigorates people like me and the rest of our Caterpillar team when we see some of the innovation that you're able to bring forward and some of the things that you can be creative and do. And so it's very exciting for us, and it really makes me feel like I want to go back to work and do some really cool stuff again, you know. So thank you for that. So, and now we're going to go ahead and announce the winner for automation in the program, and just say thank you.
So first, we're going to have, if you go to the next slide, perfect. I'm going to have Matt Fike come up. Matt's a engineering manager in our automation and autonomy organization, and he is going to talk about the results of the RC efforts and who's the expert lunar operator. Now, before Matt does that, just a raise of hands, how many of you got the chance to run CAT RC either at the UCF or at KSC? Nice, nice. Well, Matt, I'll turn it over to you.
All right, I still have a couple hats to give away, so who wants to make a little noise to get some hats? All right. Thanks, everybody. All right, so if we want to get another slide here. So, sorry about the technical difficulties with the machine a little bit. So we only had a few teams come through, but I do want to have the top 3 teams come up and grab a prize. So each person from the top 3 teams can come have a pick. And so we'll start out with team number 1, got first place with 11 minutes and 22 seconds, is We Yearn for the Mines. Jacob Evans Zachary. All right. Yeah, grab 3 things for your team. Just pick something, it's all right. All right, number 2. Just a little bit short, Purdue. 11:56. Go, guys. Great job. All right, and in 3rd place, UNH Lunacats. Are we here? All right, if the Lunacats aren't here, let's go to 4th place for some prizes. So, all right, 4th place, the Shish Kebab with College of DuPage. College of DuPage, anybody? All right. How about the Swoops? Anybody from the Swoops here? Yeah, there we go. All right, guys, thanks so much. Hope you enjoyed running the RC system. Check us out. Go search Command for Dozing or CAT Command Station. You can see all about our product. Thank you so much.
Thank you, Matt. The Caterpillar hats are always in demand. That was great. If we go to the next slide. So now we're going to get into the exciting part with the Caterpillar Autonomy Awards. If you go to the next slide. So here are some of the high-level results from this year. How teams, this is just how they scored with the highest level, not their total points, but it gives you an idea of the levels of autonomy that teams have been able to achieve here at UCF and at KSC, because it's the sum of the two. And we had 12 teams total out of the 35 that were able to perform at some level of autonomy. If you go to the next slide. And so, one more. Big celebration, because that's over 30% of the teams. All right, so a big round for everybody. Next slide. So before I get into 6th through 1st place, I want to make reference to the honorable mention teams, the other teams that scored points but did not make 6th through 1st. So if you go ahead and click again. So College of DuPage, School of Mines, Texas A&M, University of Utah, University of Portland, and the United States Military Academy. So congratulations to all of them for being able to achieve some level of automation and autonomy. If you go to the next slide. So beginning with 6th place at $250 is University of North Carolina at Charlotte. John, do you want to come up and help me? Hand out. Next slide. 5th place, also at $250,000. Boy, don't I wish? Yeah. Boy, there goes my, yeah. Wow, there went my bonus check for like a decade. Is University of Illinois, Chicago. Good luck. Scott, bro, get up here, bro. Get up. Bro, get up. Okay, next slide. Fourth place, not $500,000, but $500 is Michigan Tech. And third place, $750 is University of Akron. Wow, okay. And second place at $1,250 is University of Alabama. And first place, $2,000 is Purdue University.
We gotta get software up. We gotta get software right up here. Pull here.
All right. Thank you, everybody.
That is awesome. Congratulations to all the teams who won Autonomy Awards. All right, next we are going to give the award for the efficient use of communications power. The efficient use of communications power essentially means the team whose robot did the most on its own, right, without having to communicate back to the students in the control room. And so the team, and we have a certificate and that we'll give you here today, but I believe we also have plaques that will be sent in the mail for most of these awards. The Efficient Use of Communications Power Award goes to University of Utah. Great job. All right. I would like to bring Rob Mueller up to the stage for the next set of awards. Rob Mueller.
There are lots of parts to this competition, but the core of it is the Robotic Construction Award, and that means building the berm robotically. But remember, it's not just the volume of the berm. It's tempting to say that's the biggest berm, so that must be the biggest score, but that's not really what happens. The mass of the robot matters, the power it uses matters, the level of autonomy matters, and the volume of the berm all matter. So just keep that in mind. The scoring rubric is what counts, not just the size of the berm. So given that, I'll get right into it. The Robotic Construction Award, third place, is awarded to the University of Alabama. The Robotic Construction Award, second place, is awarded to the University of Utah. Okay, the top prize for Robotic Construction Award, first place, is awarded to the University of Illinois in Chicago. All right, so there's lots of dimensions to this competition, and we've just awarded all the individual categories, so congratulations to all the teams. And when you aggregate everything, you get the Artemis Award, and the Artemis Award, it takes into consideration all of the components of the competition, including the systems engineering, which is one of the most important parts of this competition that's not very visible, right? It's work you do ahead of time. It's not something you do here. But it is a big part of this competition, and it counts towards the Artemis Award. Okay, late breaking news. We did have the judges team triple check this, because you know how spreadsheets are. So we did check it very closely. And as I was saying, this is the overall prize, so it's everything considered. And that means outreach, systems engineering, and also the construction. So it's my honor to announce to this group here that the Artemis Award for the 2025 Lunabotics competition is awarded to the University of Utah.
Almost there. Thank you. Wow. So, is Rich in the room? Rich, do you want to come up here and help us wrap up this ceremony?
Hi guys, my name is Rich Jonabeck. I'm privileged to lead a fantastic group of people out here who made all this happen for you guys. All right, these are all volunteers from across the agency, from private industry, Caterpillar, Sisloon, Rigel, all these wonderful folks, the Astronaut Memorial Foundation, who made this happen for you guys. And take this, move forward, do better, do good things with it. To close out, NASA's SwampWorks are the primary sponsor here at Kennedy Space Center who helped out. So I want you to give a big round of applause for all these wonderful people who helped this out. If you took advantage of the seminars that were held here, we had systems engineering seminars held by Atwater, we had Caterpillar, we had the winner of the Australian Rover Challenge out here from Queensland University of Technology from Brisbane. I hope you had an opportunity to talk to these people. You're going to learn good things from them. I hope you had a wonderful time out here. Thanks for being with us. Kurt, you want to close it out?
Eric Reiners from Caterpillar has a special way that he would like to close out the ceremony. Eric Reiners.
All right. So we started off with a Lunabotics shout out at UCF, and so as we all head home and safely get home, let's do one last Lunabotics shout out on our way out. So if everybody stands up. I'm going to count down from 3. Now, do you know what we're going to do? NASA Lunabotics. You're going to have to do it louder than that when we do it, right? We want to rock this whole place here, all right? Are you guys ready? No. Are you ready? Yeah. 3, 2, 1. Design it, build it, dig it. See you next year.